In this lecture, we will continue with discussing the linear models for classification. So unlike in the previous case in regression, where our target vector would be achieving some particular values, maybe a scalar or a vector valued, in this case here, we will be classifying the target output into several classes, and such that each of the data elements is assigned to a particular class. So as in the case for regression, we will have an input vector of some input values. This could be also scalar values, but it could be also vector values. And each element is therefore a d-dimensional data element, and it corresponds in the training set to observations t, so that is the target vector, where of t1 to tn, so the same amount as the input vectors, where each tn is corresponding to an xn input, and it has a slightly different structure than the previous t target vector. It will have a structure of binary values of several dimensions, depending on how many classes we have. So for example, if we have 5 classes, k equals 5, then the target vector will look like this. We'll have 5 elements, and each of these target vectors in this set, and it will define that a particular input value is a member of a particular class CK. So, for example, in this case, it will be the member of the class C3, where this is a non-zero value. In fact, it is the binary value 1, and everywhere else it is 0. So this is association with a certain class is expressed by this k-dimensional vector. And in case of probability distribution, it can be seen as an extreme case of probabilities, where for the known training data, we know that it is associated with a certain class, therefore the probability is 1, and for other classes the probability is 0. And the goal is to train our machine learning representation to predict the class corresponding to a new value of input vector x. So which of these classes does it belongs to, depending on the neighborhood information where other values from the input vector have been already trained, and we will assign a class membership with a certain probability distribution to this vector x. This is for the probabilistic models, where the tk, as I said, expresses the probability of belonging to the class CK. And that would lead that this input space, where the input vectors x live, is divided into decision regions, and these decision regions will have decision boundaries. And for like linear classifiers, these decision boundaries will be therefore hyperplanes. It will be d-1 dimensional hyperplanes in d-dimensional space, defined by these d-dimensional data elements. However, as we discussed earlier in the chapter 1, there is not only the possibility of having a probabilistic approach to solve classification. We can have generally two approaches, which is one is dealing with a non-probabilistic approach, where we simply have a discriminant function, and this discriminant function decides to which class a certain element is assigned to. And then we have a probabilistic models of classification, which are based either on the discriminative or generative models using conditional probability P of ck given x. So we will be discussing first the discriminant function approaches, and then we will move to discriminative and generative models. So we will be discussing linear models of linear classification. So the linear classification generalizes the linear regression, where we have the simplest linear regression is defined as the weighting of the input dimensions of our input vector x with a vector w, and then plus the bias term w0. And this is in fact the linear regression part, but in the classification, the linear regression value comes as an argument to a nonlinear function f, which is also called an activation function. And this activation function will assign some value to this regression argument, which will then be used for defining the classification of our input vector x. The decision surfaces correspond to a yx which are constant values. So along our decision surfaces, our yx would have constant values for different input values x, but it will always have the certain value c, as we will see in a moment. Then these are linear functions of x, and therefore it will correspond to these hyperplanes, which are d-1 dimensional, even if the activation function f is nonlinear. We will be using primarily the example where the basis functions are simply just linear regression, is simply a linear regression, but all discussion will be valid for basis functions of a certain of a higher complexity, and we will be returning to a more general formulation later, where we are using the basis functions phi in our regression term, which is an argument of this activation function. So for k equals 2 linear discriminant function, we have that this corresponds to a two-class classification. So either something belongs to a certain class or it doesn't belong to a certain class, which we can say that it belongs to the other class. So input, let's say x belongs to C1 if the yx is bigger than 0 and C2 otherwise. And if yx is equal to 0, then that will lead to the fact that we will have a constant value and we will be on the decision surface. So, and we can see from this formula that the decision boundary is in fact bigger equal, so we will be assigning all these elements to the class C1. So as discussed, we will be defining a d-1 dimensional hyperplane in the d-dimensional space. Now, imagine that we have two different x values input vector, xa and xb, and they are both on the decision surface. So for both of them, it holds that yxa is equal to yxb, and that is equal to 0. So they would be belonging to the class C1, but they will be really on the boundary here. And we, at the same time, we can express that as these are both equal to 0, we can also perform their subtraction. So yxa minus yxb equals 0, and that can be reformulated because yx has this formula as as w transpose times xa minus xb, and so we will have the w0 for both of these terms, which will cancel each other out, but this is equal to 0. So now, if this is equal to 0, however, xa is not equal to xb, so we will have here a regular non-zero vector, and if one vector is dot product with another vector is equal to 0, it leads to the fact that these two vectors are perpendicular to each other. This means that the vector w is in fact, our weight vector is in fact perpendicular to our decision surface, to our d minus one dimensional hyperplane. It's actually, it forms the a normal vector, not necessarily as scaled, it's not normalized, but it will form a vector which is perpendicular to this d-dimensional hyperplane in the d-dimensional space. Let us have a look at the geometric interpretation of our regression function and the weights w and the bias term w0. So if we would set with our yx for a particular input vector x is equal to 0, that means that we are on the decision surface. Then it also means that this term is equal to 0, and therefore the w transpose x is equal to minus w. And we can normalize it by the vector, by the magnitude of the vector w, of our weights vector, and that will lead to the so-called normal distance from the origin of the decision to the decision surface. So we can see here that we have our decision surface here, dividing it our space, 2D space, into region 1 and region 2 for each class 1 and class 2, and the vector w, if it's if we divide by this vector w and effectively we normalize these weights so that the weight vector will be in fact normalized. In sum, its length will be 1. Then this distance will correspond to minus w. So we can see here that this is the distance, and if our vector w will be normalized, it will be just minus w. So this is the one geometric interpretation, how far our decision surface is from the origin, as the bias is pushing our decision surface away from the origin. And then we have also the another interpretation of the so-called signed distance measure from the decision surface by value. So we can see that our decision surface is defined by y equals 0, and everything what is higher than 0 is this half space, everything what is smaller than 0 is this half space. And therefore, we can define some input vector x as its projection onto the decision surface, so x perpendicular, plus the vector w, which is normalized here, so a normal vector to this decision surface, or in this 2D case decision line, scaled by some scaling factor r. So we can see this geometric interpretation here. We have here the some point x, input vector x, and this input vector x, it has a projection as x perpendicular here, and then its value is achieved by this vector here, which is parallel to the vector w. So it's the w vector scaled by some factor r. We don't know this factor r for a moment. Now, if we have a look at this equation and we multiply it by the w weight vector and add the w0 on both sides, we will see that the left-hand side is then equal to our yx, and for the right-hand side, we multiply this term with the w and add the w0, and we can see that this term w transpose x perpendicular plus w0 will be in fact the y for x perpendicular. So it will be the value of y x perpendicular here, and then we will have this residual term here, r w divided by the magnitude of the vector w. So as we take these terms and these terms for the y x perpendicular, so this term, what is its value? It's actually 0, and therefore we will have a value of so what will remain here will be the w transpose w divided by the magnitude of w. And we know that w transpose w is the dot product of w will result into w squared, and divided by the magnitude, it will be the magnitude will remain in the numerator. So our final value will be that the yx is equal to r times the magnitude of w. If the w would be normalized, if we will have the w normalized, then the yx will be directly equal to r. Otherwise, the r is equal to yx divided by w. So we can see that the yx forms the signed distance measure, and in case the w is normalized, then it is not only distance measure, but it's a Euclidean distance, the signed Euclidean distance from the decision surface. Now, we have been treating the w vector, the w0 separately, but we can add to our input vector x the component x0, which will be 1, and therefore the x extended will be equal to the vector including the x0 term, and therefore in such a case we can do that also for the vector w, where it will be extended by the w0, and in such a case our yx is equal to extended W transpose extended X. So we no longer have the bias term explicitly mentioned here. The geometric interpretation of this is that we can see this as a d-dimensional hyperplane in d plus 1 dimensional space, expanded space, where this d-dimensional hyperplane goes through the origin of this d plus 1 dimensional expanded input space. So that was the discussion about the classes, two-class classification, and we can also extend it to the classification to more than two classes, to k classes. In such a case, our target vector will no longer be either 1 or 0, but will be equal to the vector of zeros and 1, 1, which will be indicating the class it corresponds to. Now, if we would think that we can combine the two-class discriminant function for the case k is bigger than 2, we will see that some straightforward extensions will be problematic. So let's have a look at the two cases. One is 1 versus the rest, meaning that we have k-1 classifiers, so not only one decision boundary, but k-1 decision boundaries, each separating points that belong to a certain class ck from the other points. This is delineated here, where we can see that one decision boundary is defining as all points which belong to C1 and all points which not belong to C1. And then we have here another boundary for C2 for all points that belong to C2 and all points which do not belong to C2. That's the region R3. So we have kind of three reasonably clear regions, but with this type of discriminant function with k-1 classifiers, it leads to a region which says that the input points here are both classified to belong to C1 as well as to C2. And we know that our classification problem should classify each our input point into one class, not several classes at the same time. So that will be problematic. Another idea which we could think of will be to have a 1 versus 1 classification scheme where we will have k times k-1 divided by 2 binary discriminant functions for every possible pair of classes. So, for example, we can have a discriminant function which will separate as a linear discriminant between having a function belonging to C1 versus to C2. So is the point belonging to C1 or C2? This will be the discriminant function answering this question. And then we can combine it logically with another discriminant function, which will be discriminating the values C1 and C3. So for here, we have these three different categories, three different classes, and then the C1 would naturally belong to this half space. C2 would naturally belong to this half space, and C3 would naturally belong to this half space. However, again, we have a problem with a certain region where we do not know whether it belongs to a certain category or not, because here it explicitly says these all points above this line belong to C1 with respect to C2. And making it an end condition with this category, we will see that we are now limiting this space here with C1 versus C3, but there also this region belongs to. So it is, this region would say that it belongs to C1 and at the same time doesn't belong to C1 with respect to this condition, and this condition would say that it belongs to C1. So it is ambiguous whether this region, elements of this region belong to C1 or C2, because it doesn't, and if we look at the condition C2, it should belong to C2, but here it also says that it should belong to C3, and here it says that it should belong to C3. This region, however, should not belong to C3 because it should belong to C1. So in this, there is a region where none of the input vectors of this point actually belong to any of these three classes. So it will create a problematic region. This can be solved by having a single k-class discriminant in the way that we will have k number of y functions, our linear discriminator functions, and each of them will have lead to a certain value for a given point x. And once we have this certain value, we can then evaluate for which of our y functions, y1 to 1 capital K, is this value the highest. And the highest value will basically define us to which class this point x belongs to, without any ambiguity, because we simply take the max. So we can see it here that we assign x to the ck if ykx is bigger than yjx for all j is not equal to small k from 1 to capital K. And the decision boundary between ck and cj is where the ykx is equal to yjx. This will create a linear discrimination boundary, and we can see that if they will have certain generally non-zero value, but as they are equal, if we will perform a subtraction of these two, they will be equal to 0. So this term times, so this weights for one discriminator and another discriminator subtracted form us another as a kind of a subtraction of the weight vector transpose x plus the subtraction of the two bias terms will be equal to 0. So this is the discriminator function. Single k-class discriminant would be able to assign our x input vector into any of the k classes according to this approach. Now, it will actually lead to a decision regions, Rk, for each class. The discriminant region will be singly connected and it will be convex. So these decision regions will look approximately like this. And we can see that they are singly connected, so the Rk is singly connected, and it is actually also convex. We will see, for example, that if point xa belongs to Rk, and at the same time point xb belongs to Rk, then their linear combination of these input vector points, input points, will also lead that all of the points on the linear combination of these two will be also belonging to the region Rk. Let's have a look at to see clearly that this is true. We see that we have our x hat is equal to lambda xa plus 1 minus lambda xb for lambda equals 0 to 1. So this is a linear interpolation between these 2 points. And the yk of x hat is equal to lambda times ykxa plus 1 minus lambda ykxb. Because if we put this into the yk, we will have this formula in the argument, and then as we have this formula in the argument, we can also multiply it out with our w, and we will have this as a result. Now we are saying that the xa belongs to the rk, therefore the function yk is bigger than function yj for the same point for all the functions j, where the j goes between 1 to capital K, except of the small k. So if we now subtract yk from yj, it will be always bigger than 0. Similarly, the same holds for the yk with respect to the point xb. So it's again it's biggest for any of the compared to any of the yj functions, and then therefore this term is again bigger than 0. Now, if the point y, the x hat belongs to the rk, then this term would also need to be bigger than 0. And this term, if we now reformulate it, so we just express it in terms of the linear interpolation, it leads to the following formula here, where the lambda is multiplied with the difference between the ykxa and yjxa, and the 1 minus lambda is multiplied with ykxb minus yjxb. And this term, we already have seen here that it is bigger than 0. It's positive, this term. And this term is also positive. And this is some non-zero value, or between 0 and 1. And this is also some value between 0 and 1. So, therefore, for sure, this term will be also positive. And that means that this holds, and that means that the x hat is also within the region Rk, in the decision region Rk. Now that we know how to set up the classification in terms of the decision region, that we need a single k-class classifier, we can turn our thoughts on how to train a discriminant function. Let's have a look at the simple approach of least squares and analyze whether we can use it for classification. So in the least squares, we would have some input vector or input points in the space, in the d-dimensional space, and we will have k classes, and these k classes will be described by target vectors, which each point will be defined by some binary code consisting of zeros and a single digit 1 in the vector, and we will see whether we can learn this classification in a similar way how we learned the least squares for regression. The idea is not completely irrelevant, although it sounds like there is no real value here to somehow corresponding to the like a target value corresponding as in case of regression, but rather a binary code of one of k binary coding scheme. But however, the least squares are approximating the conditional expectation E t given x of target values given the input vector x. So that somehow indicates that we might get a reasonable classification scheme. So in our setup, we will define our function y, which should perform the classification. So this is a vector of functions from 1 to capital K, and remember the one which will result in the highest value, highest positive value, will be then assigned to the particular class. So we are having here this extended representation of our weights, and we have here our extended vector x. Why is this a matrix now? Because we have a set of functions. So we are not having only y1, let's say, but also y2 and y3 and so on. So, and for each of the rows, we would have a different y. And then we want to find the matrix W extended by minimizing the sum of squares. So we know how this approach should be done, and we will see it on the next slide. So our error function containing now the extended capital X, which is the entire set of X input points, so where the nth row is defined by the xn, so the data point, the nth data point. And our error term can be written in this matrix formulation as 1/2. So we remember the 1/2 for this error data term. And we have here now the trace of a matrix, which is a product of a transpose matrix with itself. So we know that such a matrix will be actually symmetric, and therefore we can also reformulate this into a slightly different formulation so that we can better understand what this trace really means. Well, trace is an operation on matrices where we simply sum up the terms along the diagonal. So here is a reformulation of the same thing, where we have the matrix, which is the product of this matrix multiplication, and we are interested only in the diagonal entries, the k entries, 1, 1, 2, 2, 3, 3, and so on. And this can be reformulated into now a double sum, where we are having this x extended, w extended minus t, and squared, but we are interested in squaring the term nk term. So where we are going from n equals 1 to capital N, k going from 1 to capital K. And this is basically the formula which we are using. So if you want to perform a square sum of all elements in the matrix Ij of a matrix as a product of its transpose with itself, then this is basically the formulation. In other words, if we want to sum up the squares of all elements of a matrix, it corresponds to the trace of the ATA. So here we can see that this is the square of this of all elements within this matrix, and because we can see that these are the elements within this matrix here, individual elements, and those are all squared, so we sum up all the terms within this matrix this way. So this formula is in the book, and we can now clearly see what is the underlying meaning given this matrix calculus explanation. Now we want to set the derivative of this error term to 0 as always, and therefore we can do it here, where we see that we are performing the trace of this square term. And but before we do this partial derivative operation, we can see here that this term, this square term, can be multiplied out, and it will end up in these three terms. One, the first term, and the second and the third term, as we would expect. So this multiplied with this, or this transpose with this, then the cross terms, and then t or minus t multiplied by transpose multiplied by minus t is here. This all, if we perform the derivatives, then we want to perform the derivatives of these individual terms, and this term doesn't include any w, therefore it is falling out from these partial derivatives already, because it will be equal to 0. So we perform the trace, as this is, we can separate it into two trace operators, and therefore we will calculate the partial derivative of this trace. For that, we will again use the results of matrix calculus, which are written here. So we can see that if we have a W transpose a W, and we are performing partial derivative with respect to W, then this is equal to AT plus A W. And so this term here the W is here, the A is equal to X extended transpose times X extended, and therefore the result here is, after the derivative of this first term, which is X extended transpose times X extended plus the transpose of that term times W extended here. Now for the second trace here, we again use another result of a matrix calculus, where the partial derivative of the trace of some matrix C times the matrix W is equal to C transpose, and we can see that this is our C, and therefore this will be the C transpose, which is the T transpose X extended transpose is X extended transpose times T. So here we have the formula, and this will be a symmetric matrix, and of a symmetric matrix we know that the transpose is the same as the matrix itself. Therefore we will have here twice this X extended transpose X, and the twice will be multiplied with will be cancelled out with this 2 here, or this 1/2 will be cancelled out with the 2 coming out from this term then. And we also can see that this 1/2 is no longer in this term, because we are here summing up this term and this term, which will create 2, and then that will cancel out the 1/2. So as a result, we will have the formula which we also obtained from the linear regression, where we have the X transpose X W is equal to X transpose T. Now I did mention the extended parts, and that means that the W is equal to X transpose X inverse times X transpose T. So this is like the result of linear regression in the matrix formulation. And this will result in the closed form, and we can simply obtain out of that the values for the matrix W extended. Once we have that, we can calculate for our new points, so not part of our training set, their classification, and that will be done by calculating it for each of the y's. So we will have the vector of y's, and then we will find the maximal value of the y among the y coordinates, and then that will be corresponding to the particular class which the x belongs to. So, and here we can just see that the W transpose will then result into this formula times the x extended, but also we can have just the row vector x extended and then multiplied with the matrix from the left. Then we can notice that as the target vector Tn, for example this one, as we already have seen it, fulfills an interesting condition. It fulfills that for particular A, so vector A plus B, this is a scalar, it equals to 0. So for example, or for A equals just a vector of ones and B equals to -1, for any Tn, we will have that this equation will hold, because the ones will just multiply with zeros and with just 1. So the result of this dot product here will be 1, and -1 will be equal to 0. That means that once we perform our closed form and we define our yx, we will be having a fitted least squares model, which will also satisfy this linear equation for any x, the a t y x plus b will be equal to 0. And the result will also be that the sum of the yk functions or classifiers for the individual components will be equal to 1. However, in this discriminant function, we are not dealing with probabilities, and therefore it doesn't mean that the sum will be equal to 1 like from probability values, because it may and will often happen that the yk doesn't is not just from the 0-1 interval. It will be negative often bigger than 1 or -1, and therefore it cannot be treated as probability distribution, but it will hold that this value of the sum of the individual function y components will be equal to 1. Now, the least squares are a possible way to go for classification, but they are not a very good suitable solution. So the least squares will learn one discriminant function and for k classes, and then however, like we have here for 2 classes, however, it is we will see that it will fail in many cases. So for example, it is not very much robust to outliers. Here we have an example where it works reasonably well. The green is the so-called logistic regression, which is much more robust, and purple is our least squares classifier. However, it works here, but if we look in the case where we added some more very clear members of the class, blue class, we see that these outliers, which are much clearer on the side of the actual um, decision region, they will bias our classifier so that the decision region will change. So for the least squares, this decision region will change, and we will see that some of the blue dots will be actually appearing in the region of the red points. And therefore, we would not see that this classifier is a very fortunate one in that regard. And the reason is that it corresponds to the maximum likelihood under the Gaussian conditional distribution. And we know that these binary target vectors of the k entries with 1, 1 follow the so-called categorical distribution, which is the special case of the multinomial distribution with n equals 1. So, and therefore, this assumption does not hold, and therefore we can see that the overall suitability of the least squares for classification is not very fortunate one. Here we see another example where we have 3 classes, and these 3 classes with the logistic regression will be nicely linearly separable from each other. However, in our case of the least squares, the classifier will create as the following decision regions, where we can see that the middle class here will be in fact distributed into the red and blue decision regions. With the least squares case, we are quite sensitive to the outliers. So it can easily happen that some of our points, which belong to one category, are misclassified due to the effect of the outliers. However, in case we have a well-separated, linearly separable classes, we can also think of it in a geometric sense, how to generate the discriminant between that will separate these 2 classes from each other. So the main issue is that our approach with the least squares does not necessarily secure the maximal class separation. And we are looking into the Fisher's discriminant, which is the key idea to geometrically kind of find the linear decision boundary that maximizes the between class separation and minimizes the within class separation. So what does this mean? It tries to put the 2 classes as much as possible from each other, but doesn't want to separate the elements or points or members within a class. So, and in this separation, we know that we are separating these classes with, in the case of linear classification, with a d minus 1 dimensional hyperplane. So in case of 2 dimensions, for example, like we can see here, we have these 2 classes, and our separation will be done by a line between those. So ideally a line which looks approximately like this. So, and in fact, what we are interested in, that after we perform the separation, how much are these 2 classes separated by this discriminant after the projection. So we can see that we are projecting from a 2-dimensional space onto 1-dimensional space, and we see that these 2 classes, red and blue, are reasonably separated already. However, there is still some class overlap happening here. The strategy for the between class separation can be understood as trying to identify the means, the centers of our classes based on the data, and then separate these as much as possible. So if we look at this, this is the MK is in the data space. It's the mean of each of the class distribution, and then we geometrically connect these two centers, and our separation, the discriminant, is basically defined as orthogonal to this line segment that connects the two centers, and it is going through the middle point between those. And with this, we can already achieve some nice separation. Now we are interested in the projected class separation. So that is what at the end matters, that our discriminating function is creating two classes in this projected space, and this projection happens by the dot product of our weights and or linear combination of our components of our means with the weights vector. And as we know, a line can be described by various values of W, such that they could be multiply of themselves. So therefore, we are defining the sum of the weights to be equal to 1, so that our weights vector is normalized, and the MK does not become arbitrarily large. So in case we would have isotropic classes, meaning that they are basically two distributed on kind of a circular shape or Gaussian, isotropic Gaussian shape, then that would mean that this separation is, which we have just described, so connecting the centers of these two distributions, and then finding the center bit on the line segment and finding the separation line will lead to the best separation between these two, and it will be maximizing the term M2 minus M1, which is the projected class separation, which can be computed as the dot product of the weights and the vector M2 minus M1. An observation is that the W is in fact proportional to this vector. So this is a vector from M2 to M1 or M1, M2, and our W vector of the weights is basically having the same components as these two, as this vector, up to the scaling vector. What does that mean, and why does that come to place? First of all, we can see it geometrically, because here the W is we know that the vector W is perpendicular to our discriminating line or plane or hyperplane in more dimensions. So, so what is perpendicular to this line is actually the M2 minus M1. So our W geometrically is proportional to this vector. We can see it also from the other perspective, that we are trying to maximize the separation of the means of different classes. And if we are performing it through the dot product will be maximal if these two are parallel to each other, these two vectors. That will be the highest value. And if they will be orthogonal to each other, it will be equal to 0. So therefore, the dot product also algebraically reveals that the W for maximal separation needs to be proportional to the M1, M2 vector. However, for an isotropic class distribution, this separation based on the between class separation is not sufficient, because we can see that the separation here is not perfectly aligned with the anisotropic shape of our classes. So therefore, in our previous case, we see that we are still misclassifying some of the members of the blue class and some of the members of the red class. Therefore, the Fisher's linear discriminant is defining a discriminant function in the following way, where we are maximizing the between class separation and minimizing the within class separation at the same time. So, and that can be performed by forming this discrimination function, or a function which characterizes how well the current discriminant is separating, where in the numerator we have our between class separation formed by the square of the projected between class or projected centers of our classes, and then in the denominator we have the within class separation formulated in the following way, where we see that we have the yn. So what is the y? The y is the projected points. So the y corresponds to a certain x, where the x, the yn is equal to w dot product with the xn. So this is the projected points, and these are the projected means, and we want that this distance is then overally minimized. So we do not want to have high projected variance. We want that the variance for each of the classes is as small as possible. So here we have the projected mean somewhere for the red class, and here we have the projected points of the based on a particular projection direction, and we want to find the direction under which this variance after projection is minimized. So this term characterizes this variance for each class, for class 1 or for class 2. And we sum up these two within class variances and have forming the denominator of this expression. So then by maximizing this term, we will be maximizing the between class separation and minimizing the within class separation. Now we are reformulating this because we want to find the corresponding W vector. We are formulating it here by representing these projected quantities into their the formulas which lead to that projection using the W. So here we have the W dot product M2 minus M1, where we previously saw that if this will be the only governing principle, we will end up in this situation. But we have also this denominator where we see that we are summing up the individual distances. Essentially, this is the projected variance for class 1 and projected variance for class 2. And that we can multiply out and reformulate in such a way that we end up by taking out, for example, the W from this square term and having it, so this squared is like a dot product with itself, and that dot product with itself will have therefore such a form where we see that we have the W's at the at the beginning and end, and we have this the M12 vector multiplied with its transpose, so forming actually, so this is a dot product and this is a dot product, but here, so as at the end this will be a scalar value, but here we have the matrix, which is interesting to separate from the W because we want to look and find the W. Then in the denominator, we are looking at the also separating the W, which we have done here, getting it effectively out of the sum, and we can see the corresponding formula here. So what we have done here, we have put these two sums into forming one matrix. So this is the variance matrix calculation within class variance, and which is in this formulation in the object space or input space, and with multiplied with the dot product of, or the dot product with W, it will lead to the projected space. And we can see that in the similar way we have both the W on each side, and because it was constructed in the same way as in the numerator. And now we can observe that we can identify a certain matrix here as B, which is the matrix which separates the or characterizes the between class separation, which is here, and then we have the matrix as W, which is characterizing the within class separation. So this is basically our formula for the characterizing the degree of desired separation between and within classes. So now we want to maximize this term, and we do it by performing the derivative of this function, and then we perform the we set it to 0. So we perform derivative with respect to W of this quotient here, which is equal to the original value of in the denominator times the derived numerator minus the original numerator times the derived denominator divided by the denominator squared, as we know from calculus. Now, the derivative of this expression in matrix calculus would lead to 2 times SBW, and the same will be for the case of the 2 SVW will be the derivative here. And this should be equal to 0. Now, for that, in order to find out what should the W vector be in the maximal case, we can, for example, get rid of this denominator, multiply it on both sides, and then we will have only this term. And we will therefore be looking for what the W has to be. And the in the ideal case, the W will lead to a separation as shown in this picture, where we have minimal variance of the projected classes, and we have also the maximum between class separations. So we still would go through the center of these two classes, like of the point between these two classes, however, under slightly different angle, which is minimizing the within class variance. So now we have the term here, which was supposed to be equal to 0. Now we put one part of the term on the other side. So this term should be equal to this term. Now let's have a look at what these terms are. So essentially, this term here is just a scalar, because we have here a multiplication of the vector with a matrix, and that is then, or let's say here we have a multiplication of a vector with a matrix, which leads to another vector. And then we see here the vector transpose times vector will lead to some scalar value. So this is a scalar value. This here, of this term, this is a vector transformed, vector W transformed by the matrix SB. And a similar observation can be made here, where we can see that this vector is vector transformed by the SW matrix. However, here we can see that we again have, this is the product of these two is a vector, and the vector transposed by vector is again a scalar. Now, we do not really care so much about the magnitude of the W, because we can always constrain it, and we will constrain it to have a magnitude 1. What we care about is the direction of the vector W. So and it can be its components of this vector can be scaled by arbitrary scalar value for each component. Therefore, we can just put these quantities on the other side, or in some sense get rid of them, because imagine that we take this scalar and put it on the other side. So we would end up with a statement that SBW is proportional to SWW. So multiplied with the between class separation, the W should be proportional to the multiplication of the within class separation, aggregated within class separation matrix times W. Now, another observation is that SBW is in fact just, we said that originally that the W is proportional, for if we do not consider the within class separation, to the vector M2 minus M1. And in this case here, SBW is equal to the SB times the W. Now, if we look at this, we can see that this term here is again a dot product of one vector with another vector. So it will lead to a scalar. And therefore, the SBW is in fact proportional to the M12 vector. So we can see here that the SBW is proportional. So therefore, we can conclude that M2 minus M1 is proportional to SWW, and from that, so after the multiplication of the W with this transformation matrix SW, we will actually have it aligned with M2 minus M1, but the vector W itself will not be proportional to this, but it will be proportional to SW inverse times M2 minus M1. And this is the result. This is how we can obtain our weight vector using the Fisher's linear discriminant method, which takes into account the between class separation and the within class separation. For we have now defined the W, but we do not know the bias term yet. And that one, so we can just plug in the resulting W, maybe we, as I said, normalize it so that the magnitude of W is equal to 1. And then we want to find out the W0, which bias, which will lead to the fact that everything every y for an x which is bigger than this y0. So if we are having this is the separation point, if you like, for all points this of the x which are belonging to the category 1, we will be above the y0, and for all the points C2, we will be below the y0, the projected point of the on which lies on the line. So if we imagine the previous illustration of these two classes, we know the direction, but we don't know the bias, the offset, and we need to basically find out, like if we have a certain direction like this, like how far is it, and we can find that corresponding W vector, the W bias, so that these conditions are fulfilled. Now let's have a look at how does the Fisher's linear discriminant relate to the least squares we have been discussing before. So in case of the least squares, we have our error term, which we are trying to minimize. And in this case, we have previously defined that the Tn is either equal to 1 or 0, depending on if it belongs to the category 1 or class 1 or the class 2. Now we will slightly change this the values which the T will be obtaining in case of belonging to the category 1 or in case of belonging to the category 2, and we will actually find out or show that the Fisher's linear discriminant is a special case of the least squares approach if we give the T some special values. So the T will be not 1 if it belongs to the category 1, but it will be n divided by n1, where the n1 is the number of elements belonging to the category 1 from our training data, and then the T will be equal to minus n divided by n2 if it belongs to the category 2. So as we see that we always need to have some kind of a value associated with T to indicate a membership to a certain category. We have previously chose 1 and 0, but we also can choose other values as we have done now. Let's have a look how does our least squares develop if we have these two different values representing the class memberships. So for the least squares, we of course would like to perform the maximum likelihood estimation to estimate the corresponding values for W0 and the vector W, which will be minimizing this particular error function. So, and we do it by means of derivation and then which is set to 0 to find the extreme values. So in case of deriving with respect to W0, we will have the following equation, because we have here 1/2, and the derivative of this term here will be 2 times this term times the anything what is associated with the W0, which is only 1. So it will lead to this term, and we will cancel out the 1/2 in the front. This should be equal to 0, and therefore we can see that we can take out the W0 from the sum. So we will have n times W0, and then we will have the vector W transpose with the sum of our points, which is somehow representing the average, but the average scaled by the number of points. And then we have this last term here, which is in fact telling us what is the Tn. So imagine the Tn for particular x and belongs to the category 1. So if it belongs to the category 1, the Tn value will be n divided by n1, as we have defined it here. And how many of these Tn's will be in this overall sum? Well, there will be n1, because the amount of members which belong to the n1 are to category 1 are n1. So therefore we can take it out from the sum, and we will have here the n1 divided by n1 times n for the category n1. Now we can also look at if we take out the Tn from this sum, how many Tn's will have the value minus n divided by n2, and it will be n2 of these terms, because we have n2 members of category C2. So here again the n2 cancels itself out, and we will result here in n minus n, and that is equal to 0. So the whole Tn part will cancel each other out, and therefore we will end up in a term where we have the only this part is then equal to 0. But therefore we can put one part on the other side, like for example this part divided by n. By the division by n, we create the mean point of the overall distribution. So our W is equal to the minus W vector transpose times n. So that is for the W. Now, so this is the W, which will be the for which we will have the least squares will be separating the two classes, or actually will be fitting the values of the classes the best. And then we have our another term here, which is the minimization of minimization of the error term when with respect to the W. So we are performing the derivative with respect to the vector W, which leads to of this function, which leads to then the Wx. So again, these two will cancel out with the 1/2 here, and then the multiplication of the dot product of the W transpose xn derived will lead to xn. So we end up with this term here to be defining our derivative, which we set to 0. Now, again, what we can do now is to separate this sum into the sum of the two categories, so that we see shortly the two categories separately. And what we can see here is that we can then put the actual value for the Tn. So here we have the category 1, therefore the Tn is always n divided by n1, and here it's in this other sum for category 2, it is n divided by n2 but minus, therefore we have here the plus sign. And these terms we can now take out from the respective sums, and they will lead to, again, so this will be n1 times, this will be n2 times by taking out of the sum, so the n1 and n2 will cancel each other out, and we will have the sum of xn, because we take not only this term, but of course multiplied by xn, and we will lead, this will lead to the mean of, because we will have the xn here, will be taken out, and it will be n1 times this overall term, and therefore we are cancelling and so the n1 times will be leading to the fact that we are creating here actually the mean value, because taking out this xn out of the sum will be like taking out the n1 times the m, and then it is multiplied with this, and the n1 will be cancelled out, so we will end up with m1 here, but minus, because this term is negative. And the same will happen for the for this term. So the sum of xn is equal to n2 times the mean, and therefore we get out here the mean multiplied by n2 and with n divided by n2, and the n2s are cancelling themselves out, and the m2 will be associated with the n. And so both m2, so we will have the expression n times m2 minus n times m1, and we can put it together, and we will have this expression now here. And now we have taken out the tn's from this sum, and we can put back these two separated category sums together for the rest of the terms, and we will see that this is the formulation here. So we no longer have the tn in the sum, but what has changed here is that we have replaced the w0 with the minus w transpose m. So the m and xn are both multiplied with the w transpose, and therefore we are putting them into the as a common term, which is multiplied with the w transpose. And then we have the xn as before. So here we have performed two operations, taken out the tn and also replacing the w0 with its respective maximum likelihood estimate. And now we can change the order here in this calculation, because what is here is essentially a scalar product multiplied by a vector. So the outcome here will be some vector, and we can therefore reshuffle the terms. So here we can see that this term, which is here, can be represented by multiplying this term with xn transpose, and and the W T is then multiplying this actual matrix. So it's a vector matrix multiplication, which would lead to a vector as we want. And also we can in fact change the order and take out the W from the sum, and by that we will have this term here, which is a sum of xn minus m times xn transpose, and this whole matrix after the summing up all the xn terms will be multiplied with the vector W. And then, so this is equal to this, and together this should be equal to 0 for the maximum likelihood estimation of W. So we are not finished with this term yet. It involves several not complicated, but multiple operations to reveal what this term actually is. So let's have a look at that. So we have here the term now without the multiplication with the W, and that term we can realize it as separating again into the two classes, which have identical content for now, and then now we see what we can decompose this into. So if we represent this term, we can add plus minus mi, so the center of each category, each mean of each category, and that will lead to this entire term, where we will have the xn minus mi times the xn transpose, and then we will have mi minus m times the xn transpose. So we are making out of this one term two terms which are outer products, sum of two outer products, in which we have ones minus mi and in another one we have plus mi. So they would cancel each other out, and therefore we can expand it this way, and it's equal. And once we have done that, we can also see that this term xn minus mi xn transpose, so in fact this term here, is equal to, and now we are representing this xn transpose by xn minus mi and then plus mi. So it will be equal to xn minus mi times xn minus mi transpose, and it will be equal to plus another sum xn minus mi times mi transpose. So we have again created xn minus mi and xn plus mi. So these two sums will be equal to this one. And this sum, in fact, is like we have here the sum of xn minus mi, and we know that for the class 1, the sum of xn will be basically n1 times mi, and this is also n1 times mi, so therefore this term will be equal to 0. So we end up that this term here is equal to this outer product formulation, and therefore we have we can put this formula to this part, because we have been it represents this part of the term. Now for this part here, we are also seeing that we can we are representing here, because this is a sum of mi, this is a constant value for the entire sum. What is the only thing which is changing is the x, but the sum of xn's here is equal to ni times mi. So for the category 1, it will be n1 times m1, as we said before, and then transpose. So we simply cancel out this sum, and we have this expression now, and we can reorder the terms so that we have mi minus m times mi transpose. So by that, we have formulated what is this term, which we multiply the w with. It is equal to this term plus this term. So that is what we can observe here. Now, if we take into consideration both of the classes, because we have solved this for like for each class generically, and now we put the actual classes into the place. So we have the first term of the sum of outer products, which is this here, and we have it for both classes, so we slightly rearrange, and then we have for one class this term, and for the another class this term. And this in sum is equal to, in fact, if we observe it, it's the same as our matrix SW, which we have been discussing before in the case of our Fisher's discriminant. So these are the within class variances. And now it remains to be said what are these two terms. So let's have a look. So we can see these two terms, and we will now replace the m by a value which is calculated from the individual m1 and m2. So our m is in fact equal to n1 times m1 plus n2 times m2 divided by n. So imagine that we are summing up the xn's of one class, we are summing up the xn's of another class, so we are summing up all the xn's, and then we are dividing them by the n. So this is the term which is characterizing it. Now, if we want to put the m1 onto the same fraction, then we multiply with the denominator, so this is n times m1 is, so this expression here is this expression in the brackets, and it is times n1, and from the right hand side times the m1 transpose. And the same we will do for the n2, where we have the another class. So n2 is times m2 minus m times m2 transpose, again is equal to the m here and the m2 multiplied by n here. We form one fraction, and then we observe what is happening. So n times m1 minus n1 times m1 is in fact equal to n minus n1 times m1, and n minus n1 is in fact equal to n2, because n is equal to n1 plus n2. There are only points belonging to category 1 or to the category 2, and their sum is equal to n. So n minus n1 is n2. So we have here an expression that n 2 m1 plus n2 m2. And here something similar is happening. N times m2 and here minus n2 m2 will be n minus n2 is n1. So we will have n2 m2 minus, sorry, n1 m2 minus n1 m1. And this whole is multiplied by the n1 and here n2. So we will in fact have a term here which is n1 n2 and then m1 minus m2 divided by n for one of these terms, and again multiplied by m1 transpose. So here we put the n1 on the same into the same fraction, forming this fraction here multiplied by the vector m12. And the same is happening here, where we have again the same term, and n m1 minus m2 transpose. So these two terms are identical, only these two transpose means our vectors are different. But we can put them together and forming this term overall. And this term, we can take out the transpose and put it into the onto the bracket, and we will this will lead us to this outer product here, m1 minus m2, m1 minus m2 transpose, which we know is the between class separation matrix multiplied with this term. So that leads to the fact that now we need to backtrack several steps, but we will understand that the derivative of the error function from the least squares with respect to w and set to 0 is equal to n m2 minus m1. This came from the tn's values, and then we have the rest, which is the sw plus n1 n2 divided by n times sb multiplied with w. So, and this is equal to 0. And therefore, we have the term where the SW, this term here, and the basically sum of these two matrices multiplied with W is equal to n times m minus m2. Okay, so let's have a look at what the W will then be at the end, and we can see the following. If we now just look at the SB times the W multiplied with some term, is in fact if we put it, let's say we put it on the right hand side, we realize that the SBW we have previously said is in fact the proportional to m1 minus m2. So we can formulate it in a way that it's proportional and up to some constant c1, this term with m1 minus m2. And we have m1 minus m2 also here. So it's just another constant. So this will form a sum constant c2. So we will come to the conclusion that the SW times W is equal to the C2 M1 minus M2. And that leads to the conclusion that the W is proportional to SW inverse M1 minus M2. So we ended up with the same outcome for what is the vector W using least squares as we found out with in a slightly different approach with the Fisher's linear discriminant. So the Fisher's linear discriminant is a special case of least squares where we assign special values to the output values t, namely n divided by n1 and minus n divided by n2. And this holds for the two-class classification task. So far, we have been talking about the Fisher's discriminant in terms of discriminating between two classes, but this discriminating function, which comes out of the Fisher's discriminant approach, can be used also for multiple class separation, as long as they are linearly separable. And in that case, we will simply have to expand slightly the characterization, where we will no longer have the weights of just one separation line or generally hyperplane, but we will have several of those, and they will each be characterized by one of the vectors as a part, which is part of the matrix W. So the vector of these projected points will be the multiplication of the weight matrix with the input vector. And for that, for Fisher's discriminant, we need also the centers of our means of our individual classes, which we calculate in the same way. And then we have the overall mean, which is calculated in the same way how we would calculate the mean of input points. Or we have another formulation here. It's like sum of k over k classes, nk times mk divided by n. That's what we had before. On the previous slide, we used this formulation. And our within class variance is in object space, or in the input space, is equal to the sum of this outer product, where we have the mk is the mean of the each class. Now the sum of the within class variances is the sum of all these individual classes variances, as we had before. And then we also can define a total variance, which is, as we would expect, and as defined, xn minus m times xn minus m transpose. So as we know from before, this is the variance, and actually this total variance can be calculated as a sum of the within class variance and the between class variance. And we already know what is the within class variance, the total one, which is here. Therefore, the between class variance can be calculated from the total variance and subtracted by the within class variance. And if we do it, we can see that here we have the mk, we have the m here. So naturally, this SB will lead to an expression which involves the difference between mk and m, and this is all nk times. So for each class, this term will be appearing for each class nk times, for kth class nk times, and therefore the between class variance is a sum of this outer product between the class mean and the total mean multiplied by the number of members in each class. So now for the multiple classes, we have expressed both the SW and also SB, and from this we can further calculate the Fisher's discriminant functions. So for the Fisher's discriminant functions, for the multiple classes, we will also define the covariance matrices in the projected space, in the Y space. So we are projecting now onto using the hyperplane onto a hyperplane where we want these classes to be maximally separated. So there, the after this projection onto the Y space, we calculate, so where we have the values Y, which are obtained from the matrix W times Xn. We have the means of each class defined in this way. So this is after the projection. The overall mean is calculated as a sum of the means multiplied by the nk and divided by n. And therefore, we can express the term here, the projected within class variance, as the sum of the yn minus mu k for each class separately, and then summing up over all the classes. So this is within the class k variance. This is with over all classes, is the s small s w, which means it's the after the projection, and the sb is equal to the nk and then mu k minus mu, analogously to the original input space. And it's these two projected these two matrices which are characterizing as the degree of separation, and not in the input space, but the ones in the projected space. And again, we want to maximize the between class separation and minimize the within class separation. That can be done by multiplying these two matrices. So this is SW inverse times SB. And in fact, we are looking for the trace of this matrix, of the result of the product of these two matrices. And the trace can be understood as that this matrix holds eigenvalues which measure the between class and within class separation along each direction in the subspace. And it is the sum of these eigenvalues which this trace is measuring, and that's why we have this trace operator here. Therefore, we are interested in maximizing the trace, and that will maximize the sum of these generalized eigenvalues, leading to the maximal class separation and minimizing the within class separation. This is in the projected space. We can also turn it back into the input space, as we see that, for example, this term here, if we replace the y with w times x, and similarly the mu k would be w times the mk, we will find out that we have simply the input space within class variances multiplied by the matrix W, both for this term and also with the matrix W for this term. Therefore, we will have the matrix W on both sides of this term for the within class variance, and the same holds for the between class variance, because this projected version of the between class variance can be represented by the input in the input space, but it will be multiplied with the matrix W on this side and also with the matrix W on this side. So therefore, we have this result here. So we can maximize the input space variance and the between class variance product here in the input space, which comes from this projected space counterparts. So this concludes the discussion about the Fisher's discriminant, and now we will look at the last possible function which can form as the class discrimination, and that is the so-called perceptron. The perceptron algorithm is characterized by having it's a two-class model, so it can only separate two classes, and it includes a feature vector in the generalized linear model. So now we no longer have here input x, but we have the phi x, which is the feature vector, which are some given basis functions. And then this term, so the linear combination of these basis functions for each input vector, are then input or argument of the function f, which is the activation function, which will be, if the argument inside is bigger than 0, it will be +1, and if the argument is negative, then it will be -1. Similarly, the t equals 1 will correspond to all the elements of the class 1, and the t equals -1 will be characterizing all the elements in the class 2. For completion, we have also the weight W0 and the corresponding feature basis function phi 0x, which is a constant 1. Just that we can multiply the W0 with 1 and have it all in one term. So for the perceptron algorithm, we want to iteratively learn the weights W, so not in a closed form solution, but iteratively by the gradient descent, and it should happen through the learning through the error function minimization. Now, what is an error here? Error means that if we have some misclassified patterns, so the capital M here is the number of misclassified patterns, and that represents an error. If one point is misclassified as belonging to the different class, that's an error, and we want to minimize this error. So this would be a natural choice for error function. However, it will lead to a piecewise constant function of W. So we change W, and then there will be some set of misclassified patterns. Then we slightly change it. It will not change anything. Then we change it until it suddenly, this amount of misclassified patterns abruptly changes. So it will be constant functions of W if the number of misclassified patterns is the desired error function, and it will have discontinuities, and therefore there will be zero gradient in these constant regions, and then there will be these jumps between once the misclassification changes. So we would like to have some smooth error function instead, so that we have a gradient well defined on this error function, and therefore we can use it for the iterative approach of learning the weights W using the gradient descent approach. So therefore, we are using the perceptron criterion, where the perceptron criterion comes from the following insight. If we have our classification, if it's correct, then we have the outcome of this term will be bigger than 0, and we have, so this is a correct classification, as only in the case, so this is bigger than 0, if it belongs to the category 1. And for that, we have the Tn must be equal to 1. So, or the correct classification will be that this term is smaller than 0, so it belongs to the other category. And in that case, the Tn must be minus 1. So no matter which out of these two terms is the case, in both cases, the product of the Tn with the dot product of the weights with the feature vector, it must be equal or bigger, greater than 0, because here it is positive times 1, and here is negative times minus 1, so it's always positive. Incorrect classification means that we are evaluating some feature with a feature function and the learned weight vector and multiply it with the Tn, but we end up in this, let's say, being positive, this being negative, or this being negative and this value is positive, which is the mistake, and that will lead that this product is just smaller than 0. So our function, which we want to minimize, the perceptron error function, will be sum of all the misclassified patterns where we have here this product, which is negative, as we know. Therefore, negative negative times negative will be positive. So we want to minimize this sum of misclassified patterns. And this function will be smooth, unlike the other function which we discussed before, the just number of misclassified patterns. So now, therefore, we would need to perform the gradient descent and perform the derivative of this error function. So our error function will be defined as adding up the misclassified patterns, and it will be a linear function of W, but the contribution of the corresponding correct patterns will be equal to 0. So this is only a sum of misclassified patterns. And we want to use this error function in the gradient descent approach, where we are iteratively finding the vector W, where we have in each time step, we update our weights vector. And the update is by this learning rate multiplied with the gradient of the error function, and the error function gradient is in fact the feature vector times the Tn. And we only perform this update if we have a misclassified pattern. So without the loss of generality, if we assume that this eta learning rate is equal to 1, then we will be basically updating this weight vector with the feature vector. So that means that we will always, because either this is positive and this is negative, or this is negative and this is positive. So either way, we will be adding to the weight vector this vector, which is in the feature space are the coordinates of the points xn. So let's have a look at this in an example. We can see that the perceptron algorithm and the gradient descent work in the following way. We have our training points, this blue and red points, transformed into feature space. So they are not this is not the input space, but they have been already transformed by this basis functions phi. And here we can see we have the origin of this feature space, and in this space we have also our vector w, which is defining us. This is the vector w, this black one, and for the w tau, the time step, and this is therefore the discriminating line, or generally hyperplane, which is separating us the space, feature space, into two half spaces. Each half space should be containing only one class if is this linearly separable. So we perform a classification, and now in case we have a misclassification, like for example for this point here, our gradient descent is requires an update, and therefore, so this is non-zero value here, and therefore we will be adding to this w this vector. And so what we can see here geometrically, that we have this is the vector phi xn from the origin to the point. So these are the coordinates of the point in the feature space, and we add that to the current weight vector, which is here, and we can see that with that we generate a new weight vector, and this is this vector where we changed both of its magnitude and also its direction. And this is after the first iteration, and then we are having as an input another of our training points. Again, it's misclassified, so this point should be red, but the red region is defined that it's here by the feature vector, sorry, the weight vector direction, and therefore we again take from the origin the direction towards our feature point, and these are the coordinates of the feature point, and we add it to our weight vector. And therefore, now our weight vector will maybe slightly change the orientation, but it will flip the direction it is pointing to. And at this point, when we will take any of these points, we will have a correct classification, and therefore our weight vector will not be updated anymore, and we will converge to this discriminating line characterized by this weight vector W. And we can see also algebraically that this converges, because we can see how does the function of the y, which is this part of this expression, times the tn, how does it change over time? So we can see that this term is somehow it's a misclassified pattern, and then however in the error function, and then this error for this particular point only, not it might make the classification worse for some other points. However, we have here in this, so this is after t tau plus 1, this term is equal to the w vector tau t phi x and tn, and minus, and we have this term, because this term is the update of our weight vector. So this is we separate this vector w tau plus 1 into two terms, where one is the previous weight and the update of with this feature vector, and this is also multiplied by these terms to complete the error term. And however, this term is positive because it's a squared term, and the squared term is therefore bigger than 0. So therefore, this term is smaller than only this term, because this term is then made smaller, the error. So this is in case of error, this is a negative term, so this is a positive term, and the error with increasing error, this is growing, and here too. And if we subtract some positive value, this positive value will become smaller. So this value here, positive value, is smaller than this positive value before the update. So it means that the error will for sure be evaluated for the particular point. The error term will be less after this update than before the update. But as I said, it only holds for the end pattern, and it can easily happen that by the update for the xn, we will introduce a misclassification of the points, some other points. So, however, the perception convergence theorem states that the algorithm converges if there is a linear separation between the two classes. And if it is not linearly separable, it never converges. However, the disadvantage of the perceptron algorithm is that it does not generalize to the classes more than 2, and it is based on a linear combination of the basis functions. Let us turn the discussion from the discriminant function approach to classification to a probabilistic approach. We have two different approaches for probabilistic approach for classification, and one is using the generative models, and the other one is using the discriminative models. So now we will first have a look at the probabilistic generative models for classification. So the decision boundaries, which we will be looking for here, will be coming from the assumption about the data distribution. So we will assign it a certain model, the data distribution, like, for example, a Gaussian distribution. So the generative approach models the class conditional densities as the Px given xa, and the class priors, so the probability of a certain class, to compute posterior probabilities, P probability of a certain class given a certain x. So we are modeling the class conditional densities here and the class priors, and with that we can then define the posterior probability, and the posterior probability is then used for calculating the probability of a certain class, and then the higher probability will be then assigned in the classification for the making the minimal error in the decision, as we were discussing back earlier in the decision theory part. So let's start with discussing a two-class classification, and we can have a look at how do we calculate the posterior probability of C1 given X. So that is calculated by having the class conditional probability of X given Ci, and then the class prior. divided by this what we also previously termed as evidence. So this normalizing term, where we have the sum of this class conditional probabilities for each classes multiplied with their respective priors. So for two classes, we have a sum of two terms here. Now, we can also change this expression slightly by just dividing by this term on the top. So both the numerator and the denominator. So we will have 1. Here we will have also 1, and here we will have this fraction, the px given c2 times pc2 divided by px given c1 times pc1. And in fact, this function is, if we perform if we define a certain quantity a being the logarithm of this expression, or the its reverse, then or a reciprocal, then we can express this term as an actual function which we already know, with an exponential term here and minus a. So minus a means that it will flip into the correct way then after this minus. And then this is actually a function which we know, this is the so-called sigmoid function. So our posterior probability will be actually governed by a sigmoid function, where we can see here that the sigmoid function goes from x equals minus infinity, or a equals minus infinity to plus infinity, and it will be assigned value with the sigmoid function between 0 and 1. So the posterior probability equals the logistic sigmoid, which squashes the real axis into the interval 0, 1. There are some identities associated with the sigmoid function, such as the sigmoid of minus a is equal to 1 minus sigmoid a. And if we invert the sigmoid function, we will achieve the so-called logit function. So if we look at the definition of the sigmoid function, this is therefore this implies that if we perform a reciprocal operation on both sides, that 1 plus e powered by minus 2 is equal 1 divided by sigma, and then the furthermore we express this as 1 divided by e powered by 2, and then we put the minus 1 on the right hand side, and we will soon realize, so then we perform a reciprocal of this, and logarithm that the a is equal to ln sigma divided by 1 minus sigma. And this is the so-called logit function, which is inverse function to the sigmoid function, and expresses the log odds or log ratio of probabilities, as we have seen in the previous slide, because this a was formed by this logarithm of these posterior probabilities for each class. And for the k equals 2, that was the case. For k is bigger than 2, the posterior probability equals to the so-called softmax function, which is also termed as normalized exponential. We can see here that we have the multiplication of the joint probability of x and ck in the numerator, and then we have the normalizing term, the evidence, which is the sum of joint distributions of the x and all the respective classes. And that can be characterized as the sum of ak divided by the sum, e powered by ak divided by sum of e powered by aj, where the ak or aj is equal to ln px given ck and times the probability of the prior of the class. So for j, the index will be just j instead of k. So, and we can see that this function, this softmax, is again a smooth version of max function among various classes. And for ak much bigger than aj, it will lead to that the posterior probability distribution posterior probability will be close to 1 for very high AK, and it will be close to 0 for the much smaller AJ. So we can see this for also graphically. Imagine that we have our probability distribution. We model the class probability as a multivariate normal distribution. So our pxck, so the class conditional probability, is modeled as a normal distribution and as multivariate normal distribution as we know it, with the scaling factor here and the exponential factor here, where we have this square term expressing the necessary parameters, the multivariate mean and the covariance matrix capital sigma. So, and we can see that for the conditional probability or posterior probability will be actually for two classes corresponding to the sigmoid function of a linear argument of the weight vectors W. So, and the weight vectors W will be coming from the as a parameters from the normal distribution of one a mean of one class and another mean. And here we have a case where we have the same covariance matrix for both classes. So this is a kind of a special case which is relatively easy to understand, but we will see that this will lead to a linear function here, which will lead to a linear discriminant between these two functions, between these two probability distributions, which we are modeling by the normal distribution. And the W0 will be equal to this term, where only in the last term is actually expressed the prior probabilities. So the prior probabilities, together with some other terms, will be leading to the bias. So the direction of our linear discriminant will be given by the vector W, which is independent of the prior, and only the bias, the offset, if you like, of this linear discriminator will be dependent on the priors of these respective classes. And we can see that if we have here these Gaussian distributions for the class of red elements modeled, so it's generative, and for the blue elements, then the discriminative function, our sigmoid function, is shown here, where it is will be associating these values with a very high probability to the red class, and here with a decreasing probability of a red class and increasing probability of associating these values with the blue class. So how did we come to these values? So why is it linear? Let's have a look at that. So for now, we understand that this is the class conditional probability which we model as a normal distribution where the both classes have the same covariance matrix. So let's start with putting the conditional the posterior probability into a certain ratio, which is like the A, which we have been expressing before, but before we perform the logarithm operation. So this ratio is equal to the ratio of the uniform distributions values, and here where we have this class conditional probability and the probability prior of that class, and we know that these terms in the class conditional probabilities are equal to this a normal distribution. Now we have now cancelled out both from numerator and the denominator the scaling factors, because in fact they are both for both classes equally the same, so we can cancel them out. So we leave only the terms which are different, of course, in the numerator and the denominator. After performing the logarithm of this, we end up with the term where here is part of the numerator, here is part of the denominator, and we keep the ln of the priors as a separate term. And these terms we can now multiply, like we have here this formula where we simply perform the multiplication of the x with the x or x transpose with sigma inverse, and then with x, and then with the cross terms, and then the mu1 transpose sigma inverse mu. So we have these three terms here. And now we can see that if we perform that for the part in the numerator and denominator, this first term will be the same, and as we have minus here, it will be subtracted. Therefore, we will have only the cross term or the square term for the mean here, and we can see that here is therefore this cross term where we are putting already together so this is the cross term which is coming from so this is like mu1 and mu2 are already put together. So these cross terms can be, which are like mu1 transpose times the sigma inverse times x, or the minus, or the x transpose sigma inverse mu. There are like twice these terms there, and they could be for both terms for mu1 and mu2, and therefore we can put them into this term here, where we will in fact cancel out the 2 with this minus with this 1/2, and we can see that we have here already some term associated with the x, and then some term which is not associated with x at all. And this could be then further reformulated by mu1 minus mu2, and then inverse of the covariance matrix times x. So this is some kind of term which is the multiplying x, so this is actually the w, and then we have this term which is independent of wx, and we can recognize here that this is in fact this w0. So the vector w is therefore here, and the w0 is here, which we now understand why, and it was not clear from the just the description in the book. And therefore this term here, which is at the same time this linear function of x, is our a, and therefore the posterior probability is equal to the sigmoid of this linear discriminator. From the previous slide, we still need to mention that the fact that the sigmoid function has in the argument a linear term, namely that x is multiplied or its components are linear combination governed by the vector w and then plus the bias term, leads to the fact that while the sigmoid function is a nonlinear function, it will the discriminant between the two classes will be a linear structure, because the argument is only having linear terms, and this means that, for example, everything which is evaluated in the argument of the sigmoid as, for example, equal to 0 will be mapped to 0.5, and everything what is mapped, what is the value of, let's say, -1 will be also some constant value. So we will have this sigmoid nonlinear function will still create, as having the linear terms in the argument, will create a lines of constant values. And there, where the sigmoid is equal to 0.5, will be actually the boundary decision line between the two classes. Now, let's turn or complete our discussion to discuss also how do we devise the arguments for the AK for the multiple classes. So in the case of multiple classes, we are not having the sigmoid function expressing the posterior probability, but we have the softmax. And now we are interested to see what is the AK one term equal to. So the softmax can be represented as the as the class conditional probability times the prior, and then the sum of the class conditional probabilities multiplied by the respective priors. And here I am now, I will be taking out all the terms which are not dependent on K or C, J for that matter. So from here we can, as we know that this class conditional density is a quotient, we can take out the normalization terms, and we will be only left with the exponent, because both the normalization terms in the numerator and the denominator are the same. And then if we are looking further at the square in the exponent, we can realize that if we are multiplying it out, the individual terms, we will find out that there is a square term with the x transpose sigma inverse x, and actually it will appear both in the numerator and also in the denominator. So this part we can take out as and cancel out from both numerator and the denominator, and then we will end up only in the term which is the linear term with respect to x, and the term which is related to the mu, which doesn't contain the x. And while we have here still this exponential form, we could then already realize that the term here will be, if we would like to put the PCK together into the exponent, we can do it with a logarithm, so it will be here plus logarithm PCK, and we will have everything in the exponent. We will realize that this exponent is basically the AK, and here we will then see that there is again a linear function, where the linear function is consisting of the weights and the bias term for each k, and then each vector wk is basically defined by the sigma inverse times the mean, respective mean of that for that class, and then we have the corresponding bias term, which involves the mean and covariance matrix or precision matrix, and also the prior. So, and we can see now the probabilistic generative models, how they would form these discriminant boundaries, the decision boundaries, and the decision regions for also the same or different covariance matrices. So here we have three classes. Two of them have the same covariance matrix, and one of them has a different covariance matrix. So we can see that we have decision boundaries between these three classes. While here it's indicated that the spread of this two-dimensional Gaussian is the same for the green class and the red class, and for the blue class is different. And we will see that if we share the same covariance matrix, like it's here, the discriminant, the boundary, will be linear. And because you remember the x terms have been crossed out, because the x transpose sigma inverse x was coming from both of these probability distributions for both classes, and that has been cancelled out. However, if we will be having different covariance matrices, then the epsilon inverse will be different for each of these classes, and therefore they will not be able to cancel out, and therefore we will have also quadratic terms in our logit function, which will be the argument to the sigmoid, and that means that we will also be able to see that the boundary of between the classes which have different covariance matrices will no longer be linear, but will be in fact quadratic. So this is a quadratic curve here, and also here naturally. And we can see that the probability distribution, the posterior probability is now decreasing, and here for both blue and red, the posterior probability is equal to the same, and therefore it forms this boundary region. And the same holds between these two classes. And in this point here, all the three classes have the same posterior probability, and that therefore it forms this boundary point. Once we obtain the class conditional densities for our probability distribution of points corresponding to each classes, and we also have the prior probability distribution for each class, we can formulate the likelihood function for a set of observations. Now, this is an example of maximum likelihood estimation of all the necessary parameters for two classes, both represented with quotients, which have a shared covariance matrix. So their covariance matrix sigma is used for both probability density class conditional densities. The prior for each class is pi, which is a value between 0 and 1, and the prior for the class 2 is naturally 1 minus pi, because these are probabilities and they have to sum up to 1. And then we have the output value for which corresponds to the class C1 is Tn equals 1. For the class C2, Tn equals 0. Therefore, we can formulate the probability of a point xn from the the class 1 is equal to the probability of the class times the class conditional density of which characterizes how likely is that the point will be at a particular location given the normal distribution. So the normal distribution is simply multiplied with the prior probability, and we can see here the normal distribution parameters, multivariate mean, and the shared covariance matrix. So we have a very similar probability of xn from the class 2, where we have again the prior and the class conditional density, where we here as the probability is therefore here 1 minus pi, and because that's the probability of the C2, and again the normal distribution which characterizes the likelihood of a given point being located at a particular location in the multivariate space. The likelihood function, therefore, of our data values, meaning the set of x vectors and the corresponding target vectors, will be, or values, will be the product of each observations, because we will see that these are independently drawn samples from these two normal distributions under a given probability, and this is then therefore powered by either 1 or 0, and here then 0 or 1, depending on what value the particular Tn corresponding to the Xn will have. So this naturally either in each product iteration, it will either activate this part of the multiplication or this part. Now, with the maximum likelihood estimation, we can estimate all the parameters of this likelihood function, namely the pi, and then the parameters associated with the normal distributions, like the mu1, mu2, and the shared covariance matrix. So let's do that. Here, first, we are performing a logarithm of this entire expression, and we are separating here first, just to make it clear, the part which is associated with the pi, and here we have the rest which is not associated with the pi and only contains the normal distributions weighted with Tn or 1 minus Tn, meaning that one or the other will be then equal to 1 or will be then not zeroed out, let's say. So once we have this formulation, we can perform from the log likelihood, we can perform the partial derivative here with respect to pi, and that will lead, so it's only relevant for this part, because here we have the pi, the ln pi, and ln 1 minus pi, so that will result into the term here Tn 1 divided by pi for this part, and for this part we will have minus 1 minus Tn times 1 divided by 1 minus pi. So this is the logarithm 1 minus pi times minus 1, so that's why here is the negative sign. And that is equal to 0. So if we reformulate that, then we have here that we put this part to the right hand side. Therefore here we have 1 divided by pi sum of Tn, and here we have 1 divided 1 minus pi sum of 1 minus Tn. Now we know what is sum of Tn. It is actually n1. This means the amount of elements which belong to the category 1 is n1, and the same here, 1 minus tn will correspond to n2. So we have the expression n1 divided by pi is equal to n2 divided by 1 minus pi. And then if we want to express the pi out of this, we will find out that the pi is equal to n1 divided by n plus 2, or n1 divided by n. This therefore shows us that the pi is equal to the ratio between the elements from the class 1 versus all the elements. So, and therefore 1 minus pi will be n2 divided by n. So it will be basically giving the probability of a class given how many of elements has it observed belonging to one or the other class. Now let's have a look at the maximum likelihood if we want to find out what will be the maximum likelihood for the mu1, and then we will analogously have for the mu2. Then we can just forget about this first term because it doesn't contain any mu, so it will be then just equal to 0, and so that will be just the constants here, and here is the only part which is from the normal distribution, which actually contains the mu's. So it's from the exponent, and as we perform the logarithm, the exponent is now down, and together with the tn, and all the terms which have been serving the purpose of scaling and normalization have been also then somehow put together into this constant term. So therefore we can now perform the partial derivative so that this constant term with respect to mu1 will disappear, and we will only perform derivative of this expression. Now, this expression, we had it already before. Derivative of that is equal to inverse covariance matrix sigma times the xn minus mu1, and this is multiplied by the tn, and this is therefore the result of the derivative and is equal to 0. Therefore, we can also, as all these terms are somehow also weighted with this sigma, we will get rid of the sigma, so multiply it on both sides of the equation, so we will not have the covariance matrix anymore, and we can then therefore form the expression where the sum of tn xn is equal to sum of tn mu1, and we know what is tn xn equal to, or better to say, we know what is equal to the tn mu1, and that is equal to n1 times mu1, because this tn will be 1 and 1 times, and n2 times it will be equal to 0. So it will be n1 times mu1, and therefore we can say that the mu1 is equal to 1 divided by n1 and times tn xn. So this will be this will be non-zero n1 times, and it will be summed up to create the mean for summed up and then normalized to create the mean for mu for the distribution, for the first normal distribution. For the second normal distribution, for the class category 2, we will have a similar result, but instead of tn, there will be 1 minus tn for weighting all the other x's, which are members of the category 2, and normalized by n2. So that will be the result of this mu2 mean. And for the last part, we have the we want to perform the logarithm and then derivative with respect to the covariance matrix sigma, and therefore we can just take out all the terms which are not associated with sigma, and we are left with few terms which are associated with sigma. So now here the ln determinant of sigma will be part of the terms which will not be cancelled out by means of the differentiation, and then also the square term from the exponent for one of these um, um, normal distributions for category or class 1, and then we have again 1 minus tn ln determinant of sigma, and then 1 minus tn times the exponent for the category 2, and finally we have this, what I just put here as a c, which are the constants which will be then equal to 0 because they are not containing any sigma covariance matrix. So after we perform the differentiation, this will lead to the following formula. Before we, however, do that, let's reformulate that this square term which we have, we will change it into the expression of the trace, and the expression of the trace can also then be reshuffling these individual parts of our matrix which we perform the trace of, and we can see here that we will do it for the one class. This is then done for the other class, so it's always non-zero if we are dealing with the other class, thanks to this 1 minus tn term. And furthermore, however, we can put these sums together, and we will end up in a trace of a matrix, which is a composite matrix, multiplied our inverse sigma here, and our precision matrix, and with the matrices which are resulting from the outer product of, in fact, the within class variances. So this is one part of within class variances for the class 1. This is within class variance for the class 2, and these are then weighted by the Tn or 1 minus Tn. So either this term is this matrix outer product is added by this into this, or the other outer product is added into the in this process of the sum. And finally, we will end up in a matrix M, which is basically this matrix here. We just substitute it with this symbol M, and now if we perform the differentiation, we perform differentiation of this n times ln determinant of epsilon, sigma, and the sigma. This results into n times sigma inverse, and then minus the other the result of the differentiation, which is sigma inverse m and sigma inverse and the minus term. This should be equal to 0, and from that we can imply that the sigma inverse times n is equal to n, and therefore the sigma is equal to 1 divided by n times m. So we can see the final outcome being here the covariance matrix capital sigma is essentially composed of the outer products characterizing the variance of the one class and characterizing the variance for the other class, and always basically the xn element is only contributing to build up of the variance of the respective outer product of the respective class where there is a member of. So this is summed up together, these outer products, and then it is then divided by the total number of the data points. So it is an average within variance, within class variance, because we will have just one covariance matrix for the actual both classes. So as we have the shared covariance matrix, it is calculated from the covariance matrices of the individual classes and averaged. So far we have discussed continuous cases of the class conditional probabilities. This means we have been using, for example, the multivariate quotient for representing the class conditional density for a certain class. Now let's turn our discussion shortly to the discrete features. Imagine that we have a vector of discrete values for the inputs. So for example, imagine that we have a case where we are categorizing emails into a spam or not a spam categories, and the vector xi would contain characteristics like does the email include a word offer? Could be one of such a feature. Another feature could be does the email continue the word money? So, and 0 means doesn't, and 1 means does. So for example, for vector 0, 0, we would have a characterization, features of the email that it doesn't contain the word money and it doesn't contain the word offer. Analogously, for an email which will have a characterization 1, 0, it will contain the word offer and it will not contain the word money. This kind of discrete features which are characterizing our scenario and can be therefore used for association with certain class membership. We can calculate the class conditional probabilities in the following way. Imagine that we have a certain probability of the something which is already an email which we know is a spam. What is the probability that it contains the word offer? And that is, if it's a spam, it contains the word offer that is associated with a certain probability. And also the same is with the word money. So with that, we can calculate if we assume that occurrence of words is independent. So we utilize the naive bias assumption. Then we can use the following product to calculate the class conditional probabilities. So imagine that we have the case offer and money, and it doesn't occur. So we will have for neither case first. So we will have this term mu k, let's say spam is 1 and I is 1, 1 minus mu 1, 1 times 1 minus mu 1, 2 will be the product for a vector 0, 0. For a vector 0, 1, it will be 1 minus 1, 1 times mu 1, 2. So this is always either 0 or 1, and therefore either this term is used in the multiplication or this term is used in the multiplication. And therefore, we will end up in each combination of the of this two-dimensional vector 0, 0, 0, 1, 1, 0, 1, 1, each of them will be associated with a certain probability. And this probability is expressing with which likelihood given an email is a spam, contains a word offer, or it offers the word money. So with which likelihood it doesn't contain any offer, any word offer or money, and when it is a spam will be expressed by the vector 0, 0. Now we can also have the class 2, which will be not spam, and it will also have the same kind of probability distribution. I forgot to say for each set of vectors 0, 0, 0, 1, 1, 0, 1, 1, these class conditional probabilities will sum up to 1. And therefore, we will have for each class 2d minus 1 independent variables. And for the, now back to the example, for the example of not being a spam, we will have also some class conditional probabilities, which will be saying if the email is not a spam, with what probability does it have, does it contain the word offer or money. And as we know, we can have valid not spam emails which contain these words too. So it will be again certain probability distribution, and this probability distribution for the second class C2 will be will not be dependent in the case of class conditional probabilities to the probability distribution of the class C1 being the spam. However, as these two are complementary, their mutual, their posterior probability distribution will be mutually exclusive. So it will therefore be complementary. And once in the posterior case, once something is with a high likelihood spam, then it is with very low likelihood and not spam. But here we are dealing generally not only with two classes, but with multiple classes. So we will be, we can take the class conditional probabilities for each class, and there we can, how do we create the posterior probabilities? Well, we simply multiply this with the probability of the class CK itself, and then we will have the resulting formula non-normalized for the posterior probability. So in order to deal with a simpler representation, we can also perform the logarithm of this formulation, where the logarithm will be from this product will be equal to the sum of these terms. So we can see that the exponents come as multipliers here, and the multiplications are the sums, and this will form our term AK. And as we discussed before, this AK will be associated with each class, and then we will use the softmax operator in order to calculate the posterior probabilities for each class given a certain x, and those that will be therefore using this max softmax operator. So all these AKs, once they are calculated for a certain vector x, so let's say 0, 0, meaning no word money, no word offer, then these will be then used for calculation in the softmax and associating for each class the corresponding posterior probability distribution. So in the previous discussion, we have been dealing either with the continuous probability, class conditional probabilities, or discrete ones. But they both belong to, as we know, to the same exponential family, where both Gaussian and Bernoulli distributions are represented, and this overall formula for these class conditional densities can be seen as the there is this a certain natural parameter which we have which we define the distribution with, and then we have some scaling function, then this normalization term g, and then we have here this exponential part. So that's why they belong to this exponential family, as we have already discussed in bigger length in the covering the chapter 2. So for this exponential family, we can generalize this our calculation of posterior class probabilities PCK given X, again still given either by sigmoid in 2 class or softmax in general for K class scenarios. So for a simpler case, let's assume that the ux function is equal to x, and then we have some scaling parameter s, and therefore our class conditional probability, then class conditional density function, will be corresponding to this expression where we have this scaling parameter represented in the individual terms of this exponential family generalization. The point is that while we will allow for each class a different lambda term, we will this characterization will share the same scaling vector s and also the function h, and in such a case we can calculate from these class conditional densities the term a, which for example in the 2 class problem will be used in our sigmoid function in order to calculate the posterior class probability. And this is, you can see, a fraction of the class conditional densities times the probability of a certain class. So it's a ratio between the class 1 and class 2. And if we perform calculation of this ratio according to this formula, we will end up in a fraction where this term will cancel each other out. This term will become, and we perform logarithm then of it, then the ax will be, here we will have the ln, and from the numerator lambda 1, and from the denominator the lambda 2, and then we will have the multiplication, or actually addition and subtraction of probability of C1 and probability of C2, and in the front we have the terms coming from the exponent for the lambda 1 and lambda 2 from the denominator, which can be put together as the multiplication or the dot product, if you like, with our random variable vector x, or input vector x. And what we recognize here is that this is again a linear function where we have a some multiplier of x and plus some constant term. So this is like w1, and this is the w0, which is characterizing this multiplication of the x, which will be characterizing our boundary decision boundary representation as a line. For the k-class problem, we will have a similar formula for each ak, and then this will be this all ak terms will be used for a given vector. Input vector x will be given to calculate the softmax function, which will then be assigning the posterior class probabilities to each class. In our previous discussion, we have focused on the so-called generative models, where we are interested in obtaining the posterior probability distribution, expressing the probability of a certain class when observing a certain random variable x or input vector x. However, in the generative models, we first modeled the class conditional probabilities. So given a certain occurrence of a certain class, what is the probability of a certain input, and multiplied by the probability of the class itself, and then we used the bias in order to find the posterior probability. First, however, we had to find the parameters of the class conditional probability before and of the prior, and then finally we were able to express the posterior probability. The advantage of the generative models is that it can be also used for generating new data from the probability of x. So if we had our likelihood function governed by the, let's say, normal distribution, we can use this normal distribution for generating new input data points. In case of discriminative models, we are no longer performing this indirection by first modeling the class conditional probabilities, but we directly determine the probabilities, the posterior probabilities of the class given a certain input vector. This has several advantages. First off, it requires much less parameters to determine, and for example, in case of this generative approach, we need to determine all the parameters associated with the distribution itself, like the class conditional densities, where, for example, we would like to know the mu for a multivariate Gaussian and the variance, and this for each class, or in at least for if the variance is shared or covariance matrix is shared, then at least the means will take a substantial space and computational effort to determine. So this is much less required in the discriminative models case, and we can have improved predictive performance, especially if compared to a generative model where the class conditional densities are poor approximations of the true distribution. So in case of the generative models, we make an assumption of how this input is being generated, and this can be very closely matching the true scenario, or it can not match the true scenario very well. And if it doesn't, then the class conditional densities will actually not be well representing the true distribution, and that will lead to a worse prediction performance. The discriminative models do not make assumptions about the underlying true distribution and directly determine the posterior probability. And with that, they might have better predictive performance. So in our discriminative models, we will be using an approach which is using the basis functions phi of x, and it will be using let's say m basis functions of phi if our feature space will be m-dimensional. So fixed basis functions means that we will not be training them in any way. They will be fixed, and they will have certain parameters which will be parameters of these basis functions. Like, for example, for the Gaussian basis functions, we will have always the mean of the basis function to be determined, and also the variance. The role of these basis functions is to transform linearly non-separable distributions to become separable using these nonlinear functions. So we can see, for example, in the example on the right-hand side, that there is no line which can fully separate the two classes, blue and red, from each other, because simply we have the red points near the value 0, 0, while the blue points are near -1, -1, and +1, +1. So this is we would need two lines to linearly separate these clusters, which would effectively be leading to three classes. So for this, these basis functions can be used to separate these classes to create just one linear separation. And for example, we can imagine that if our basis functions are based on a distance from a certain mean, and for example, we have these Gaussian basis functions here with their centers here by these green marks. So there are two, one is here and another is here. So already this one here will determine that the distance from this center, from this mean, will actually determine the membership to a class, where the smaller distances will be associated with class 1, and bigger distances will be associated with the class 2. So which we can then see also in case here that we can transform this input space into the feature space, and in this feature space we can then easily identify a linear separator which will be separating this blue class from the red class. So in addition to the feature space basis functions, we also include the special feature space basis function phi 0, which is a constant one, which is used not for the dealing with the non-separability, but dealing with the fact that we want to include into the dot product of the weights with our features also the bias term W0. However, if classes are overlapping, meaning that there will be a mixture of blue and red points in a certain area, please note that the basis functions phi in general cannot resolve such an overlap, and in some cases even the phi feature basis functions may introduce an overlap, which there where it wasn't before. So that is a certain something to be considered when designing what feature basis functions should be chosen. And then the fact that these basis functions are fixed, they have a certain fixed parameters which are not learnable, imposes certain limitations which might be or will be relaxed when discussing more advanced models later. So for the probabilistic discriminative models, we will be using the so-called logistic regression approach in order to model our posterior probability. And it is called a regression. However, it is not a model for regression. It is a model for classification. So, and in general, we can see that this posterior probability is modeled as a function y of our, which is an argument, the points in the feature space, but in fact it corresponds to the sigmoid function, which has the weighted or linear combination of the points in the feature space determined by the weight vector W. And in case of two-class classification, we will have that this class 2 posterior probability distribution is 1 minus class 1. So I already mentioned that the discriminative models have the advantage that if we have the discriminative approach, then we have less parameters to adjust. So in case of the m-dimensional feature space, we will need to find m values for the vector W, or maybe in general. And however, in case of generative model of the Gaussian, we will need to find the 2m for the means, because we will have to determine the Gaussian class conditional densities, and each class of these two classes has n means, so we have 2m, and then also we will need additional terms for the covariance matrix, which is m times m plus 2 divided by 2 unique covariance matrix entries, in case this covariance matrix is shared among the two classes. And then plus one parameter need to be also estimated for the class prior PC1 of the first class, and the parameter for the second class can be devised as 1 minus PC1. So therefore, we have much less parameters to determine in the discriminative models. The likelihood function can be defined in our case for classification as for the data of the feature points and our classification variables, so that Tn is either 0 and 1. If it's 1, it belongs to category 1, the point. If it's 0, it belongs to the category 2. And we have n observations, so we have a vector of T1 to Tn of class assignments for these corresponding points. And if we want to express the probability of such a scenario, we can model it by the probability of the y, which is our sigmoid function, powered by either 1 or 0. So if it belongs to the class 1, it will be, so the Tn is 1, then this nth element is multiplied by the is power to yn, which is the sigmoid of the W transpose feature basis functions of xn. And in case this is not the case, so it belongs to the class 2, so the Tn is equal to 0, then we are activating this part of the term where this exponent then will become 1, and we will effectively have the 1 minus the sigmoid of this of the yn. And we also know that 1 minus sigmoid is actually sigmoid with an argument negative. So that could be also the way to express it. And then as we consider drawing all these samples which have occurred as an independent process, each sample is drawn independently, and therefore we can express this probability of the target vector as the multiplication of all the events occurring with the sigmoid as the basis, as the activation function, and the phi as the basis functions. The reason why we define the likelihood function in the way as a product of y powered by Tn times 1 minus y times powered by 1 minus Tn is simply that the yn is the sigmoid function. However, it is also the conditional probability of the posterior conditional probability and of a class given a certain vector x or feature vector x. And then that's why we have determined already in the generative models that this posterior probability is actually corresponding to the sigmoid function for two-class classification problem. And here, in this case, we are simply taking the posterior probability, and in case the Tn for a given x input xn input vector is 1, then we take the posterior probability. And if it is 0, then we take the 1 minus the posterior probability, which is the posterior probability of the other class. And we multiply this together, so because each individual xn is independently drawn. And that is the probability of a t given a vector W, which we will be searching for as a part of the probability discriminative models estimation process. And out of this likelihood function, we can derive the error function, which is a negative log likelihood of negative log likelihood, which expresses into this form. So we can see that the Tn is, which was previously in the exponent, is a multiplier now, and we can see how this ln has developed into. So we keep as an argument in the logarithm the y or 1 minus y. It is also interesting to observe that this is expressing a cross entropy. So here we have an an equation for a cross entropy where we have two probability distributions, PT and QT, where PT is for us defined by the by 1 and 0 if the t equals Tn, and if it's 0 if else, and and then we have the Q n t probability distribution, which is yn if the t is 1 and 1 minus yn if it is else. So and therefore we can express by this kind of substitution or realizing what is the probability distribution of t and q, we can then rewrite this for the two variable values of t as a sum of Tn times ln yn plus 1 minus t ln 1 minus yn. So this is therefore expressing the cross entropy for the t obtaining two digits 1 and 0. So this cross entropy term is also expressing the error, because in case the Tn is something which will lead to a value of is either 1 and 0, and the y is some value between 1 and 0. So it ideally, if Tn is 1, then yn should be also 1, or at least close to 1. But if Tn is 1 and yn will be 0, then this term will be contributing to a very large error. It will be some very large negative number. And then we have, in this case here, we have a similar situation, that if Tn is equal to 0, then this term is 1, and if yn is, however, close to 1, then this term will be very high negative number. So it will be amplifying those incorrectly classified values, and this will basically express the error. Now, this error term, we can perform in order to find the W. We perform the derivative of the negative log likelihood, and here we will be we obtain the derivative of this function is equal to this sum. And how this is obtained, we will see on the next slide. However, already we can say now that this term could be used in the sequential approach for calculating the by one element by another one in the gradient descent approach. We can calculate this way the W. However, there will be some perks to it, because it actually this term yn already contains the value W, and therefore we will need to adapt this approach. However, we have it is still the W will be estimated by the maximum likelihood approach, and this generally leads to overfitting, which we could also be targeting by the maximum a posteriori approach, or taking or including a regularizer, which will then be combating this overfitting effect. So in order to calculate our error and the actually the gradient of the error, we need to have a look at the following aspects. So first of all, what we will perform the derivative of our logistic sigmoid. So the logistic sigmoid with respect to its argument A is equal to, so this is the logistic sigmoid, and then we rewrite it into a form where we have this powered by -1, and from that it is apparent that the derivative of the whole term is then minus, and the term powered by -2, and then the derivative of the exponential term inside here, which is the minus a is so e powered by minus a is minus e powered by minus a. So this is the overall derivative, which can be then expressed in this formula. And this can be seen as a product of two expressions where we take one denominator, or we split the denominator into two fractions. One is having the 1 here, and we recognize here already the logistic sigmoid, and the other one has the exp function with the argument -a here, which we can then add and subtract 1, and we will see that this term will therefore be 1, and then -1 divided by this is minus sigmoid. So the result of the derivation of the sigmoid function is sigmoid times 1 minus sigmoid. And that will be used in the calculation of the derivative of the error term, where we are trying to find so by minimizing the error, we will find which W's will, or vector W will correspond to the minimal error. So we are performing the derivative of the function which we have seen, the cross entropy function, and there we see that we take out the Tn and we perform the derivative of the Yn and the or ln Yn and the derivative of ln1 minus Yn. So ln Yn is like 1 divided by n, 1 divided by Yn, and the derivative of Yn. So the overall outer function and inner function, and this is equal to 1 divided by the sigmoid of an and the derivative of sigmoid an with respect to w, and that is equal to the result which we obtained before, so sigmoid an times 1 minus sigmoid an times the inside the derivative of the argument inside the sigmoid, which is in fact the dot product of the weights W with our feature points. And that is equal to so with respect to W, this is equal to the feature points themselves. So this is collecting this all together. We will find out that the ln Yn is equal to 1 divided by Yn times 1 minus Yn times the feature points. And we can put that back into the equation. It remains to be said what is the ln 1 minus Yn, which is very similar. We first have the derivative of the ln, which is this term. Then we have the derivative of the sigmoid minus an. So because 1 minus sigmoid is sigmoid of minus argument, and that is equal to the sigmoid minus an times the sigmoid minus 1 minus sigmoid minus an. And then the inner derivation of the minus an argument leads to the minus 1 minus 1 divided by 1 minus Yn, which is coming from here, and then this term from here, this term from here, because 1 minus sigmoid minus an is actually sigmoid an. So this is here, and then the feature vector n, but we have here this minus, which is coming from um, uh, from this term here. And so therefore our error function derivation with respect to w is therefore equal to 1 minus n phi n minus 1 minus t y n phi n. And if we are multiplying these terms all together, we will realize that we have the term tn times phi n, and then as tn times 1 times phi n, tn times minus yn times phi xn, and so on. And so we have all these terms, but this term and this term will be cancelled out, and we are left with tn phi xn and then yn phi xn. And then as we have the minus here, we can turn it around, and we end up in the sum yn minus tn phi xn as the result of the derivative of the error function. So in case of the logistic regression, we will be finding our weights w in an iterative process, which is similar to the gradient descent. However, it is the Newton-Raphson iterative optimization scheme with quadratic approximation of the log likelihood function. So it involves second-order derivatives as well of our error function. The H here is the so-called Hessian matrix, and the Hessian matrix is basically can be characterized. It could be a large matrix, but it basically defines the second-order derivatives, where the second-order derivatives with respect to the weight. So here I just have a weight 1. Coordinate and the weight 2, and it will be like a 2 by 2 matrix here, which we can see it has the derivatives by the same weights on the diagonal, and then off the diagonal it is having the derivatives of mixed weights with respect to the function e. And if we will be applying this Newton-Raphson for calculating the linear regression model, so not using the sigmoids, but having it in this term here, where we have now in our error function we have the yn. So if the yn would be the weights linear combination of the feature vectors by the weights, then we can actually land at the closed form solution by one iteration. And but however, for our logistic regression we do not have this. We have the sigmoid function as well, and that's why we will not have a closed form solution. So with the closed form solution here, we will see that the error is calculated. If we put in all the values, then we find out that in the matrix form it is equal to, we have here the weights and we have the feature vector for our point xn, and this will end up in the design matrix transpose times the design matrix and the times w, and then minus the design matrix times the vector of output vector. So this is the matrix formulation, which we can already somehow recognize that it's similar to what we were obtaining when we were finding out the closed form for linear regression. And if we are calculating the Hessian matrix here, which is second derivative of the error function, which leads to this Hessian matrix, then it's a derivative of this, and that's where we have here the with respect to W. So we will end up in the form where this is a matrix, an outer product of the feature vector, and this is basically the design matrix transpose times this design matrix, and we can use this in this formulation of the iterative methods, where the W tau plus 1 is equal to W tau minus this term, and from that we can see that this term here times this term here will form 1, and that's why we will have the W tau minus W tau, and from that we will have only that the W tau plus 1 is equal to this term times this term, and that is the known closed form for linear regression. If we are performing the same calculation for the logistic regression instead, we will see that this term will not cancel out, and therefore we will have the W on both sides, and for that we will therefore require the iterative approach. And we will see it here. We will now apply this iterative reweighted least squares approach, this Newton-Raphson, to the cross-entropy error function, meaning that we have here the yn will be equal to the logistic sigmoid, and then while this is the error function for expressed in the matrix form here, the second order derivative of it is will then perform the derivative of the with respect to the W in the y, because the y is the only part which contains the W, so this term will be derived, and this is there is no W in this term. Therefore, it will be the second order derivative will be creating us the outer product, so therefore it needs to be a matrix. So here will be this will be result of this derivative will be a vector, and this is also a vector, and together they will form a matrix by means of the outer product. And as we know, we can observe this derivative here, the Tn doesn't include the W, so it's like the partial derivative of yn with respect to W, and that is, if we know that yn is the sigmoid, it is the sigmoid times the 1 minus sigmoid times the feature vector, because the argument in the sigmoid is the W transpose feature vector, and that's the derivation from the argument. So we will have here the yn times 1 minus yn, and then the feature vector times the feature vector transpose, and this can be expressed in the matrix form as the design matrix transpose times R times the design matrix, where the R is equal to a diagonal matrix, and this diagonal matrix has the diagonal entries yn times 1 minus yn, and this means that these are the sigmoid values, which will be values both yn and 1 minus yn will be something between 0 and 1, so these terms will be positive. So that leads to the fact that these diagonal entries will be positive, and that also implies that the Hessian matrix will be positive definite. That also implies that the this that the Hessian matrix is positive definite, or at least positive semi-definite, is implies that our search for the weights function is convex. So we will be able to find our weights by the iterative approach. And the iterative approach, therefore, is calculated by the following formula. So here we have the inverse of our Hessian matrix, and here is the of the error, and here is the gradient of the error, expressed by the result we have seen previously. And if we then put everything under one, so we put the W into the equation, then this is equal to here the inverse of the Hessian, and therefore here we have the Hessian times the W tau, and minus this term of the coming from the first order derivative of the error. And that can be seen as if we put this into as one term here, this can be seen as this inverse Hessian times the design matrix transpose times R times Z, where this Z is having the R, and then here for this term we still have the design matrix times the weight vector, and then minus R inverse, because so the inverse of this diagonal matrix, because we added it here and we have to remove it therefore here, and times 1 minus t. So this is an equation which is then used for in an iterative approach in the maximum likelihood estimation for the weights W for the logistic regression using this Newton-Raphson iterative scheme. So in the two-class logistic regression, the observed label is modeled as a Bernoulli random variable, and which can achieve values of 0 and 1, being a member of one class or the other. And the expected value of the t is y, and which we are trying to find the optimal values of the weight vector W. So it's the logistic sigmoid of the linear combination of the feature vector or the feature points. And the variance of this logistic regression is calculated from the definition of a variance, where the expectation of t squared, as the t has either value 0 and 1, is the same as the expectation of t, and therefore, and this is the expectation of the t powered by 2 from the definition of variance, and therefore we obtain that the variance is equal to the sigma minus sigma squared, so the sigmoid function minus sigmoid squared, and this is equal to the y times 1 minus y. So we can see that these are also the terms on the as the diagonal terms of our diagonal matrix R. So we have here variances of the particular data point. So therefore, in the second order expansion, of our Hessian matrix will then not only include the design matrix contributions, but also it will be the contribution of the each point will be weighted by its variance expressed by this diagonal matrix R. As we have seen in the probabilistic generative models, the multi-class case where we are associating our outcomes with several classes is leading to the softmax being the function that evaluates our yk or our posterior distribution, which means that the value with the highest softmax value will be then the most, in terms of decision theory, the most preferred choice of a class. Although it will be not maybe equal to 0, but it might be close to 0, which the softmax will secure. As you can remember, the softmax has is consisting of an exponential function, which has in the argument of the e powered, the exponent, is equal to our linear combination of our feature vector entries, which in itself are functions of our input vector for each point. Now, we can see that the W vector has now has associated with K, so we have actually for each class a separate weight vector K, and that is multiplied with each of its component with the feature vectors component to form our activation value for that class, and then we are summing up all these activation values and then dividing by that summed term. So this is our posterior distribution, and also the yk, which is attempting in the ideal case for at least for the training set to be close to the Tn values. In case of multi-class logistic regression, we are not having just one value of t for representing class 1 and class 2 as we had it in the two classes, but we have actually one of k encoding, which means that we have a vector of zeros and one of the entries is 1, and we have many of these type of vectors which are then forming this matrix T, which in practice is each data point from the training set is associated with such one of k vectors, which characterizes there where it is 1 which class it is. And this probability, this likelihood can be therefore modeled as the individual posteriors are associated with each data point, and then with the corresponding transformed with the corresponding feature basis functions, and this is multiplied by the entries of the Tn, and the Tn is now a vector which consists of these zeros, and one entry is 1. So, and for all the zeros, this term will be 0, and only 1 will be 1, and therefore this product term will only choose the one for which the Tnk is not equal to 0, so which will characterize which class this particular training point xn belongs to. And all these probabilities are then associated to the particular classes are then product of multiplied together, because we are drawing independently these points. So we can say that this posterior is equal to the yk, and now we would like to see if we want to evaluate our likelihood function parameters, namely the W's, what are the weight vector entries for each of the class, we will formulate ourselves the error function, which is then the negative log likelihood. And this negative log likelihood, as we can see, has this following form, where the tnk is multiplied with the ln yk, and we can see that this cross entropy term is also forming up here nicely. So this is our error function, of which we, through the maximum likelihood estimation, will be searching for the particular values of the W's. If we do that, for that we would need to find out the derivative of this error function. So let's get to that. And as we have the yk or ln yk in the argument, we would need to know what is the partial derivative of yk with respect to ha. So, and this is the result which you can find in the book, and here we will explain how do we get to that result. So there are two cases. First, imagine that the k is equal to j, and then this term, which we are trying to find the partial derivatives of, is equal to the partial derivatives of our softmax, because that's actually our yk, and that is in fact a ratio, and we will, fraction, and we will have to therefore perform the partial derivative of this fraction. So, which means that the first is we derive the first one, and then we don't derive the second term, I mean the numerator here, as we can see, minus the first term not derived, not first order derivative, and then the second will be the first order derivative, and divided by the denominator squared. So how do we get to this? So the xak is equal to the exp ak, and then this is after derivation, and this is the non-derived part of the sum. And now in this second part, we are having, imagine that we have a sum of the various j's for all the classes, and only one is actually our class j, or which is the k here, and therefore that one is the only non-zero term. So we have here a k e powered by ak. So if we see this term, we can recognize that we can put this under different reformulation, where the e powered by ak is taken out, and here we have this part in the bracket, and we recognize that if we separate the e powered by ak divided by one of these sums, so we can split it into two equations, into two fractions, then this will form one of these sums from the square in the denominator with this numerator will form our yk, and then we will be left out without the 2 with this part of the fraction, where this part and this part will form as 1, and this part divided by this part will be forming as the yj. So here we can see nicely that for the k equals j, this is the result of our derivation. And the partial derivative, in case the k is not equal to j, we again perform the partial derivatives of the softmax, and here we can see the following. The partial derivatives of the exp ak with respect to aj is actually 0. because it's a constant term. So then we have also the second part, the underived denominator is multiplied with 0, so we lose that term. And then in the second part, we have the underived numerator and times the derived denominator, and then we will have here e powered by aj after the derivation. So we have a product of these two e's, and then we have again the square term of the sum in the denominator. And then we can separate this into two parts, and that will lead to yk times yj minus here, and that can be also reformulated as yk and 0 minus yj. And why do we formulate it this way? Simply because then for every time we have k equals j, so sort of being on the diagonal of a matrix, then we have here 1, and being off the diagonal, we have 0. So this will be in fact then replaceable by the identity matrix which we have here. And if the k is equal to j, then this will be 1, otherwise this will be 0. So this is how we came to the partial derivative of yk with respect to aj. Now we will use this in our derivative of our error function. So let's have a look at our error function. It is with error partial derivative with respect to one of these weights vectors. So for one class, let's say, as we can see here, just for one class, is actually equal to, so we have the t and k here in the front, which is this either 0 and most of the cases in 1 in the vector, and then we derive the L and yk, and the ln yk is equal to the ln yk times partial derivative of yk with respect to aj, and then partial derivative of aj with respect to wj, because these are all like the argument of the yk is then the a's, and the argument of a is actually the w. So this way we perform the partial derivative of the with respect to the weights of the class j. So this is the result. So ln of yk is derived to 1 divided by yk. Then here we know that this is now equal to, and we can see it here, yk times the identity matrix minus yj, and then aj, the partial derivative with respect to wj is, so this is aj function will be wj transpose the feature vector. So, and if we are deriving with respect to this feature vector, so with respect to this weight vector, we will have the feature vector after the derivation. So this is the result of our derivation here, and we can see that we have 1 divided by yk, here we have yk, so we can this cancel each other out. And also what we can see here, that the t and k will be many times 0. Out of this 1 to k will be k minus times 1, 0, and once only it will be 1, and therefore when it will be 1, well, it will be 1 when this k will be equal to j, and then it will be 1 because and that means that in such a case we will have the t and the k is equal to j, so t and j will be then multiplied with the 1 term here. Remember this we already lost because it's cancelled out, and then it will be t and j minus yj, but we have minus here, so we can turn it, and then the whole thing is multiplied by the feature vector of the input point xn. So this is after derivative with respect to wj. our error function, which is the first order derivative. And why do we need to calculate that? Well, we want to use it in our Newton-Raphson iterative approach, and we can use this already in such a way that we will start this weight estimation, and with this weight estimation we will update the weights taking one input point after another, and we can be using this derivative for finding the appropriate weights for a given class. Now, we are not completely done yet, because we also need the second order derivative for the Newton-Raphson approach optimization method, and therefore we need the partial derivative with respect to Wj and partial derivative of that with respect to Wk. So we use the previous result, which we can see here, where we see the difference between our estimate of the class y and the true class value t, and then multiplied by the phi feature vector. And we can see that this should be ideally, if in case of low error, equal to close to 1, this yj here. Now, if we perform the partial derivative of this, we can see that here this is the wk is not part of the t, so this entire term goes away, and we are and the w is also not part of the feature vector, so only we are actually performing the partial derivative of this function y, and then this will become a product, outer product. This vector here will serve as the calculation of the matrix with the outer product. So we can see here this is transpose, and then from derivation of this we will find that this is equal to, again as we had before, yk times the identity matrix kj minus yj and times the feature vector, and this is multiplied again with the partial derivative of a with respect to w, and with this we have reached the final value for calculating our Hessian matrix, and we can use now this Hessian matrix, or better to say inverse of it, calculated by this outer product and weighted by these scalar terms, and then this can be used together with the gradient in the Newton-Raphson method for estimating the values for the vector w for each class. For a better understanding how a iterative reweighted least squares is being performed, in particular in the more complex multi-class example, we will have one illustrative simple example which should show how this process works. The process with the two-class IRLS can be realized in the same way, or it can be simplified based on the two-class iterative reweighted least squares, which has been discussed before. So in our case, we will have only, in this trivial example, we will have only two data points, two input points, x1, which is 0, and x2, which is 1. We will have the corresponding classification, and we have, in fact, 3 classes in this multi-class example, because it should be more than 2, so it's 3. And we have the T1, which is the output vector corresponding to x1, is 1, 0, 0, which means that x1 belongs to the class 1, and the T2 is 0, 1, 0, which means that the point x2 belongs to class 2. And we have defined our basis functions, which is defined with the first, the bias, which is the first element. Here is the is 1, and the second element is simply the x, and therefore we can calculate or pre-calculate the feature vector for the point 1, which is 1, 0, and the feature vector for the point 2, which is 1, 1. Now, next, we have, this is kind of the basic setup, and we need to now perform the iterative reweighted least squares. For that, we need to find out what is our activation, and then what is our function y, which should then be similar to our true target values t, and we will then also see how we are devising the error of and the derivative of the error, the particular values, and also the Hessian matrix. So let's start with the activations. So we have here several elements, a, n, j, where n is the number of data elements, the input points or feature vectors, and j is the number which characterizes the number of elements in the feature vector. So a number of basis functions. So that is, in fact, the n is 2, and in fact for j it is also it is not 2, but it is the j is actually the number of classes. So once again, sorry, it is the number of elements n, and j number of classes, or iterator throughout the classes, because we will find out the and so in total we will have 6 elements, and the w will be the weight vector, which will have 2 elements or 2 components, and we will have 3 weights, 3 weight vectors: w1 corresponding to the class 1, w2 corresponding to the class 2, and w3 corresponding to the class 3. If we multiply each of these w vectors with our feature vector, it will give us activation with respect to the particular class. Please note that we are in an iterative approach where we will denote the number of iterations or the current iteration with the superscript here, which is the 0th iteration. Now, the 0th iteration here is initialized with the value of 0, 0. So we have all the weights currently are having the weight 0, 0. Well, that has as a consequence the fact that every activation a, n, j in the 0th iteration is also equal to 0, and that has a consequence that our y and j which is the normalized probability. So within y 1, we will be able to, for one class, first class, we will be finding out what is the probability of the point first one or the second one to be member of that class. So, but as the activation is equal to 0, e powered by 0 is 1, and here we have the softmax is also having 3 times while different activations in principle, but they also have all the same value, which is 0, and therefore we have here the y and j is equal to 1/3 for any n and any j. But let's try to understand what will this be in principle. So we can have like yn will be will look approximately, the vector yn will look approximately like vector t1 or t2. So it will have 3 components, and it's in each of the component values, there will be probability associated with a certain class. So the j are actually these components, these 3 components. So a y11, in fact, will be the probability associated of the point 1 with the class 1. And the y21 will be the probability of the point 2 associated with the class 1. Okay, so now we know we have initialized our weights, we have initialized our activations, and we have also evaluated the softmax, which has a constant value of 1/3. So it has an equal probability, each of our points to belong to any of these classes in the beginning. Then, in the next step, we evaluate what is the gradient of the error. We have already evaluated what this error is, and that is the following formula here, where we can see that we have gradient with respect to different weight j, so it is for the class 1, for the class 2, and for the class 3. And we are evaluating what is the gradient of a change. So how should we change our vector w for each of these classes so that we are minimizing the error in these iterative reweighted least squares. So we have it given by this formula, and we have calculated now the y's so that we can actually evaluate this difference to the target value, and then it's multiplied by this feature vector. So let's have a look. So now we have an iteration over all data points here, and that is a sum. So we have 2 sum terms here, and we can see that this is the feature vector 1, and this is the feature vector 2, because feature vector 1 was 1 and x, while x1 was 0, and here we have 1, 1, because the x2 was 1. And the ones, the first ones, are always the ones because they are associated with the W0 bias term. Now, what is happening in this linear term, this subtraction? So we have 1/3 for all of our y and j's. So it's 1/3, and then minus, and here we have for the first, j is 1, and n is for the first data point. So we have 1t and 1 t11, and we know that the vector t1 is 1, 0, 0, so t11 is 1. So 1/3 minus 1 times our feature vector plus 1/3, because all of them are 1/3, minus 0. And here, what is the 0? Because we have, so this is for the second, n is equal to 2. So we have 2, 1. And so this is the target vector, or the 1 of k coding for the second point, which is 0, 1, 0. And here we are looking at the first element, j equals 1. So, and we know that that is 0, because it's 0, 1, 0 for the second, for the t2. So plus 1/3 minus 0, and then multiply it with the second feature vector, feature point, and we get the result. This is minus 2/3, and then this is 1/3 here, and this is minus 2/3 are multiplied with the 1, 0, and the this is multiplied with 1, 1. So here we have here one vector which is minus 2/3 and 0, and this one is 1/3, 1/3, and then minus 2/3 plus 1/3 is minus 1/3, and then the second component is 1/3. So I have formulated it here in this form, which is effectively minus 1/3 plus 1/3. We do the same thing for the second case, and that is for the j equals 2, so for the second class. So now we have again 1/3, but then we have for the second class, we have in the 1 of k vectors for t1, we have the first one is 1, and the second one, so this is the j, the second one is 0. So times again the feature vector, that's the same thing, and here we have 1, because our t2 is target output is 0, 1, 0. This means that for the second j2 is equal to 1. The outcome of this simple sum is minus 1/3 minus 2/3 for the j equals 2. For the j equals 3, we will simply do the same thing once again, and we have here zeros twice because both target vectors have a 0 as the third component, and therefore we are multiplying this one a 1 with 1/3, and this 0 as well, but it remains 0. Here 1/3 is multiplied with each component, so we have 2/3, 1/3 is for the the gradient of error with respect to wj, 3 in this case. Now, what we do is that we stack all of these weights into just one long weight vector. So we do not have 3 weight vector gradients, but we have one, and it has not 2 components, but it has 6 components. So here we can recognize the first one, the second one, and the third one. And these are all integer numbers, but they are all multiplied by this 1/3 in the beginning. So there will be, that's their actual correct value. So now we have calculated for our iterative reweighted least squares all the necessary gradients for the first iteration, to find the first iteration of the W vectors. Now what remains to be calculated is the Hessian matrix, the second order derivative. Let's do that. So for the second order derivative, for the Hessian matrix, we have the following formula as we had it before. So the y and k is equal to is multiplied with the identity matrix component ikj minus y and j, and that is multiplied with the outer product of our feature vector or feature point. So, but what is hkj really? So it's the derivative first with respect to j and then with respect to wk. And in fact, we all again, as similar, we have what we have done with the vector of gradient, that we stack it into a one gradient vector of 6 components. We will do exactly the same for our Hessian matrix, because we will be putting our Hessian matrix into a large matrix, so that we can be updating our weights all together at once for all the 3 classes. So our Hessian matrix H, in fact, consists of several sub-matrices or blocks, if you like. So it has a block 1, 1, block 1, 2, and block 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. And these blocks we are calculating here in each of these cases. So kj will be block 1, 1. For the block 1, 1, we are basically performing second order derivative with respect to the weights w1 and w1. And so, for example, here in that case, the kj are the indices here. For this matrix, here the identity matrix value component will be 1, because we are on the diagonal. So whenever k and j are equal, 1, 1, 2, 2, 3, 3, then here will be 1, and otherwise it will be 0, because we are off that diagonal. Now that's clear. Now then we have because we have several of these indices, k, j, and n. So what are they? So the k and j are coming from which block we are currently evaluating, and then we have the value of the nk, y and k. So we have here y n is 1, so we are interested in the yn vector, where the vector yn should be similar to our in structure to the target output tn, and also as the training proceeds, the yn should gradually go towards being similar to the corresponding tn. And so the yn is a vector of 3 probabilities with respect to each of the 3 classes, and the k is the actual component of that probability vector. Now, so k is 1, but j is also 1. So here we have like y11 times 1 minus y11. Okay, so and in our y initialization, it's everything, all components of y are 1/3 anyways, so we do not really need to think which value does it have, because all of them, for both points, for all 3 classes, have the value 1/3 in this initial iteration. So here we have the y11. Now for the h11, y11 times 1 minus y11. And now here, this is our outer product, which we are calculating. And this outer product is the phi 1 times phi 1 transposed. So how does that look like? So this is a row vector, this is a column vector, this is a row vector, and now we are performing as if we would be calculating a multiplication of two matrices. So the first component is simply the first component of our column vector times the first component of our row vector, which is the only one, and then we will have the multiplication of the first component of the first vector with the second component of the row vector here, and then we switch the rows for the first vector, and the second component of the first vector has, and column vector has 0, so anything which is multiplied with 0, being the 1 in the first case for the transpose in the row would be 1, so it's 0 times 1, and this one is 0 times 0. So anyways, our outer product is the matrix 1 0 0 0 here, associated with our feature point 1, or with our input point, with our feature point 1 0, or with our input point 1, which is equal to 0 in our input space. And then, so this is the sum over our two elements, and I mean, in your case, you will not be having trivial examples, so you will have a lot of data points over this sum, so this sum will be much longer, but we have only 2 points, so that's why we are writing it explicitly, and we have here again y2 k1 y21 is equal to, again, 1/3 minus 1 minus, because this is for both parts of the sum, this identity matrix value is the same, and minus 1/3, and we have here the outer product for the second feature point, which is 1 1 column vector and 1 1 row vector here with this transpose, and again we multiply these matrices, and this will be the resulting matrix, which is having 4 times 1 as a 2 by 2 matrix. Now we can calculate what are the values here. Here is 2/3 times 1/3 is 2/9 for this, and this is only associated with this one term here, and here we have again 2/9 for all of these elements. So I decided to write it as 2/9, and then we have this, we sum up these two matrices, which is then 2 1 1 1 matrix as a result for the H11 component. And then we can, in fact, put this value already into our overall Hessian matrix, and we will have it here. So it is saying 4 2 2 2, because here we are multiplying it here with 2/9, and here we have a multiplier 1/9, so the 2 is multiplying all of these. And the reason is, as we will see, because of the outcome of the off-diagonal block. So let's have a look at another block, which is the block 1 2, and that one is the, again, 1/3, because we always have 1/3. So there is in this initial iteration, because the y components are all of them 1/3. But what is differing is that we are now off diagonal, therefore here and here we have 0, and therefore this term here is minus 1/3, and therefore the multiplication with this is minus 1/9, and we have the feature vector here, which are the same as previously, and we are summing up these two terms. We end up in the sum, which is the same value of our sum of our matrices, outer product matrices. However, our multiplier here is minus 1/9. Therefore, we have here 1/9, and the minus is associated with this matrix. So 1, 2 will be here. So we can see the 1, 1 is here, 1, 2 is here, and then 1, 3 will look exactly the same, just because we have all these this feature vector. Outer product is the same for the point 1 and for the point 2, and also the these terms here, 1/3 will be the same. And also, as we are off diagonal, we will have this 0 here and 0 here for this third term. Therefore, we will have this exactly the same block here as this block. And in fact, we will have also the same block here, and we will have also the same block here, the same block here, the same block here, thanks to the fact that our initialization of the weights all are 1/3. This will not be the case in the next iterations then, but here we have therefore on the diagonal the blocks which are also identical. So we have now calculated the Hessian matrix out of this calculation of the Hessian matrix, and we have generated this giant 6 by 6 sized Hessian matrix. However, for our iterative reweighted least squares, we do not only need the Hessian matrix, but we need, in fact, an inverse of that Hessian matrix. And that is, in fact, a problem, because by this construction, our Hessian matrix, which we have just created, will be singular. We will have a singular matrix, and therefore we need to it will not be invertible. And we have several options what we can do in order to create, to invert this singular matrix. So one option is that we use an pseudo inverse, which could be done by the singular value decomposition, for example, which will give us a nice pseudo inverse result for our Hessian matrix. Another option is that we are setting the last weight, one of the weights, to 0, 0, and we calculate our Hessian matrix based on that fact. However, that will also have the problem that as currently all our weights are 0, 0, that will not really help us. Another approach we can do is that we add a small diagonal matrix to our Hessian matrix, and this diagonal matrix will be therefore just be like a identity matrix, but multiplied with some kind of term which corresponds to certain lambda. So we basically are regularizing our Hessian matrix. And we can do it like, for example, here we can add to our Hessian matrix 1/9, and therefore we will have here a matrix where we can see that along the diagonal we no longer have 4 and 2, but we have 5 and 3 along the diagonal, except of that nothing changed. And of course, these are just integer values, and our real value of this matrix is the real value components are those multiplied with the term 1/9. Now, this matrix, once we have added this regularization term, is invertible, and we end up in the inversion of this Hessian matrix, and these are the numbers for our 6 by 6 component inverted Hessian matrix. And that one we can use in our iterative reweighted least squares in the first iteration. So we finally come to the iteration where we are calculating our weights, and our weights are that we are multiplying the our um, our Hessian matrix, and we are multiplying it with our uh, uh, gradient of the error. However, and this is a 6 by 6 matrix, and this gradient is also 6-component column vector. And here we are using still our integer values, and here therefore is the corresponding scaling factor 1/3, still from the gradient. And the outcome of this calculation can be observed as the first iteration of our weights is this column vector, where the first two values correspond to the weights of the W1 vector. Then these two weights correspond to the W2 vector, and these correspond to the W3 vector, all of them from the first iteration. So after the first iteration, we have new weights, and we therefore can have new activations. New activations, as we can see, is A11 is 2.7, and then A12 is minus 0.3 something, 1.3 is minus 2.4. And these values are already telling us like what is the point one, the input x1, what category does it correspond to, the first, second, or third? What is the highest value will determine basically the category. The highest value here is clearly the first component, so our first point will belong to the first category. And if we apply our softmax, that just translates our activations into the probability distribution among these three classes, where we can see that the probability that our point 1 belongs to the first category is 0.95, and belonging to the other two categories is much smaller. Interestingly, our activations for the second point, which belongs actually to the second category, is that the first component is again the highest, the second component is smaller, the third component is even smaller. And the normalization will assign after the first iteration that the highest likelihood where the second point to which category it belongs to is the first category. But we know that the vector T2 is equal to 0, 1, 0, so it actually belongs to the second category, but our learning approach didn't figure it out after our first iteration. Then we can calculate our gradient, 6-component gradient vector, which is here. We can see all the values of it. And I'm not putting here our Hessian matrix and the inverse of the Hessian matrix, but directly the outcome of the calculation of the weights after the second iteration, and then after fourth iteration, a third iteration, sorry, and fourth iteration. And there are still changes, but we are very slowly getting some convergence. So there will be not big changes in these numbers anymore. So if we apply this, we will realize that our weights are determining for our activations, and these activations will lead to the fact that our first point is actually categorized as belonging to the first category, and unfortunately for this learning process, our second point is also categorized as belonging to the first category. The reason why of this failure there are several reasons. One reason is that we have only 2 points, so our learning process, our training process of the weights is basically compromised by this lack of input values. And the second, our learning process basically wants to ensure that the first one is correct and at the expense of the correctness of the second point. And also, our form of regularization of the Hessian matrix might also influence this outcome. But primarily, we can see that the result of this misclassification is due to the fact that we have too few samples distributed over our 3 classes. So far, in our discussion on classification models, we have been talking about the sigmoid, logistic sigmoid, or the softmax as the classification models, where the sigmoid was used in the 2-class classification and the softmax was used in the K-class classification problems. But these are not the only activation functions we can come up with when we are considering the generalized linear model, where the generalized linear model means that we would have a linear model where we have a certain feature vector multiplied with our weights, which is an argument to the so-called activation function, which we used in the 2-class classification, the sigmoid. Now we will show that another example of a 2-class classification. And we will be looking at an alternative choice for a link function based on the so-called noisy threshold model. So imagine that we have our function an, which is equal to the W transpose and phi xn, which means that we are having a linear combination of the components of the feature vector, which is in itself a set of basis functions based on our input vector. Now, we will here in this model imagine that we are generating the data, and this data is generated in such a way that if our an is bigger than for a particular drawn sample, input sample xn, if the an is bigger than a certain value, threshold value theta, then the Tn will be 1, and otherwise it will be 0. So it will be in the class 1 or in the class 2. And the claim is that if the threshold theta is drawn itself from a probability density P of theta, then the activation function f is given by the so-called cumulative distribution function P, capital P of theta. Let's have a look how this comes to place. So we are using now still our generalized model, where we have the activation function f is having the argument the a. And we are now looking into what is the probability that a itself will be larger than the threshold theta. And that's this capital P, which is telling us the probability of a being higher than theta. But now the theta in itself is drawn from a probability distribution, so therefore we need to find out that probability, taking into account that theta is not some fixed value, but it is drawn from a probability distribution itself. So the probability that A is bigger than theta is therefore equal to an integral of the probability of A is bigger than theta given a certain theta times the probability of theta. And we are now integrating the theta threshold from minus infinity to plus infinity. Now, we can also realize that the probability that A is bigger than theta, if we know theta, is equal to 1 if A is actually bigger than theta and is equal to 0 else. And we can use this fact that this conditional probability is actually known if we know the theta, that this is 1 for every value where the an is bigger than theta. So in fact, we can take out this term and we are left with only the probability distribution of theta, and we change the borders from minus infinity to A for f. And we can see that this is basically the probability of A bigger than theta. And now this is a generic function where we do not have some specific probability distribution. And now we will put a specific probability distribution here, which will be the capital theta. And that is, in fact, normal distribution of the mean 0 and the variance equal to 1. And so we put the probability distribution here, and that leads to this equation. And you can see that this is the cumulative distribution function, which will be then the outcome of our of this function, which is a non-decreasing function of starting at the minus infinity with the value 0 and at the plus infinity equal to 1 as we are integrating the entire probability distribution. So, and this is actually the probit function, which we can also express if we have at our disposal the so-called ERF function, which is a very similar function to our probit function. And this is actually our new activation function. So previously we had the sigmoid, and this is another one. And as I said, we can, for generating it, sometimes the ERF function is available, and we can use the ERF function, which is very similar to our probit function by its formula, where there is a normalizing term, and then we have the e powered by minus theta squared d theta, where our integral goes from 0 to a. And as we are centered at the 0, it is a symmetric function. Therefore, we can make use of it so that this ERF function can be rescaled such that it will be corresponding to our inverse probit function. Our probit function is in fact will be equal to 0 at the beginning of the interval of the real axis at minus infinity, and at 0 it will be actually equal to half. So, and then the other half will be integrated over the interval 0 to plus infinity. So with this, we have obtained a new function, the probit function, which we can use for regression. And keep in mind that as it is a normal distribution, it will have here a quadratic term for our argument theta, and that leads to the fact that it will be actually more sensitive to outliers than sigmoid, which doesn't have the in the exponential function a quadratic term, but only a linear term. So what can we do with this function now? This function is simply uh, another activation function, and we can follow with determining its parameters in the same way as we did for sigmoid. So we can perform the maximum likelihood estimation, but in the way that we perform the negative log likelihood, we perform the derivative and set it to 0, and we can estimate the parameters of our probability distribution. You can imagine how this function approximately look like, because our normal distribution is just such a single lobe, and if we are performing the integration, then it will be for a long time 0 or close to 0. Then if it will be reaching 0 value on the real axis, it will be 0.5, and then again it will be integrating this second lobe as I'm drawing here. So then that from the 0.5 will therefore be, and will be very close to 1. So it will look very, very similar to our sigmoid function, in fact, but it will be driven by the square term in the exponent and not the linear term, which is the major significant difference. Now, let's turn our discussion to a certain generalization, because we might have observed that in many cases, when we are dealing with the derivative of our error term, we end up with a formula where our value which we are trying to estimate, the y, which is in itself the w transpose, and then the feature vector, or it is in the case of regression. In the case of classification, that's an additional argument to this activation function as a generalized linear model. And but in both cases, in regression, we will end up here with this, or even if our error term is square term, or the derivative will make out of it the linear term, and then it will be multiplied by the feature vector. It will be a vector because the derivative of the error function will be a vector, but it is having the same structure in case of linear regression as in case of logistic regression, for that matter, if we have the cross entropy error. And that holds not only, as we have seen, for the two-class classification, but also for the multi-class classification of the logistic regression with softmax, and we will have the multi-class entropy error. And always the derivative of the error term has the same structure. And in fact, this is a general result if we assume that our conditional distribution of the target variable is from the exponential family along with corresponding activation function. And we call that the inverse of the activation function as the canonical link function. So let's have a look at why is this the case that we have the derivative of the error term always in this structure for exponential family functions. So first of all, exponential family functions are, and now we are defining it for our target variable, t, has the following structure. As we already have seen, it has certain h function, there is a certain scaling factor here, and then we have our g function, which is also our normalizing term, and then we have the exponential part. And the normalizing term and the exponent both have a certain natural parameter eta, and the exponent itself has the random variable which of the probability distribution. Now, in this case, we have modeled the conditional expectation of the target value or variable given the natural parameters of the distribution E. We define the Y as that being this conditional expectation, and as a also the mean of the distribution, if we remember from the linear regression around where we had the bias, the noise term associated with the regression around this expectation of a t at a particular location. The expectation is equal to the t times the probability distribution. And the probability distribution of this exponential function is, in fact, we can put in this term into this probability distribution. Now, imagine that we have a function. So if we observe this function and we put it here, this 1 divided by s will change into t divided by s because of this t here. So we have this term and with the t divided by s, and such a integral is in fact equal to dt is equal to the to a derivative with respect to eta, because we can see, like, just have a look at this term here, that the derivative with respect to eta is equal to the the function here. However, this term doesn't depend on the t, so we can take it out of the integral. So once again, imagine that we have integral here of this function, but without this g eta, because we take it out of the integral. And then the only eta is appearing in this exponent, and if we perform the derivative with respect to eta, then it will, as it is multiplied here with t, it will be equal to the same term, only with times t divided by s. So that's what here we want to say, that there will be, if we derive integral of this, but however without this term, we will here have the eta will generate us the term in this integral t divided by s. So we realize that this term without the g again function is actually equal to this derivative. So this function here, in fact, is equal to this derivative, and we also know what is this derivative equal to, because we know the derivative of this function. We know integral of this function without this ts. because we know that the g eta is the scaling term. So actually the integral of this function here without the g must be 1 divided by g. So if this is therefore here we can see that this is without this ts. This is 1 divided by g, and with this t divided by s, it is actually equal to, as this expression shows us, derivative of this function, which means it is derivative of this 1 divided by g eta. So, and we can see that in such a case, our expectation is equal to g because of eta, because we took it out of the integral, and then it is equal to 1 divided by eta, this integral here. But here we see we have one extra s here, which we didn't have in the original formulation, because here is t divided by s and this is t divided by s times this. Therefore, we have one extra s here. So our expectation t given eta is equal to g eta s and then derivative of 1 of eta of the function 1 divided by g of eta. Now, this function here now is equal to, if we perform the derivative, is 1 divided by g of eta squared, because it's a derivative of the ratio, and times the, or actually of g of eta powered by -1. So here is the -1, and then it's powered by -2. And then here we still have, this was the outer derivative, and the inner derivative is the d of g eta with respect to d eta. And that is actually equal to of what is it equal to? This is equal to ln g eta times 1 divided by g eta. Why is it so? Because we can see that what is g of dg of eta divided by eta times 1 divided by eta equal to, this 1 divided by eta can be put into the d as a logarithm, because if we perform logarithm of derivative of this, it will be actually equal to 1 divided by g eta times derivative of g eta with respect to eta. So we can reformulate this term into that we put the derivative into the derivative, the logarithm. So 1 divided by g eta goes into the logarithm, then we have the other g eta here. Now, if we now dive out from this discussion, this is the term which we have here, and now it is equal to this term here. And we can see we have 1 divided by eta here, here we have eta, so that cancels itself out, and we end up with the term that the expectation of the t given eta is equal to minus s d of ln g eta with respect to eta. So we have now devised what is the expectation equal to, and we can further use it in our definition of our error term for exponential family functions. So as we have seen, the expectation, which is also y, is expressed by eta, and therefore we can say that there is a relationship between eta and y, and we call it this relationship psi for the moment. And then we can use in our generalized linear model, we can use the negative log likelihood of our probability distribution, and uh, also to find our error term. So here we have performed a log likelihood, and here is the sum of the individual target values of this exponential family function in a general way, and then we can see that this is equal to the as we have the logarithm is equal to ln g of eta plus the eta n tn divided by s, because we had this in the exponent, and then plus some constants which are associated with our scaling factors. And therefore, if we perform a derivative of this term, we will see that we have here the d of logarithm of g of eta with respect to eta, and plus t n divided by s, and then we further, because we know that eta is somehow related to y, because this is with respect to w, so we need to get the derivative with respect to w. So here is the integral with respect to eta, and then d eta with respect to y, and dy, because the y has an argument, the a, dy with respect to a, and then the derivative of a. And we can see that this is equal to, so here we see this term here is the derivative as we have as we know. And what is it equal to? That is in fact equal to y, but it's all still missing this term s, and therefore and the negative. So, but we can reformulate it here that it is y divided by s, and the negative term will make here the minus. So now we see that our derivative of this error term is getting the shape where we have here the 1 divided by s, and then tn minus yn, and then we have all these other, this c derivative with respect to y of yn, and then this f activation function derivative with an argument an, and then we have the finally with respect to the w, w transpose phi n is then equal to phi n. And now, so this is so far the term. Now we can express the relationship between the phi and the f, and in that case, we will realize how our exponential family functions will lead naturally to the to the error term which we have seen. And now, if we are taking as a canonical link function so the inverse of f of the activation function is the link function. The canonical link function should be the psi of y n. So the psi is this relationship to the natural parameter, and that implies that because the that if f inverse is equal to psi n, then if we put this into the argument of f, it is like f and f inverse is equal then to y. Now, if we have this equation here and we derive it with respect to y, both sides, then here we will have 1, and here we will have f derived outer function, and then the inner function, and this is equal to 1, therefore. And at the same time, we know that the inverse, f inverse of y is equal to a. So because fa is equal to y, therefore f inverse y is equal to a. That implies that a is equal to c. And therefore, if we just change the a here instead of the c, we have the term that this term, complicated term which we have in our error term, is equal to 1. And therefore, our error term in this canonical link function is becoming the already several times seen Tn minus yn linear term times the vector of the features phi n, and here we have a scaling vector 1 divided by s, and for Gaussian s would be 1 divided by the precision, and for logistic model the s is equal to 1. Now we will introduce an approach how we can approximate a distribution which is unimodal with a Gaussian distribution, and that could be useful for various purposes, including finding out the integral of our underlying distribution, or its at least approximation by a Gaussian that fits that distribution well. So first, let's define that we have a probability distribution Pz that is given by the Fz and normalized by the capital reciprocal of the capital Z, where the capital Z is the integral of all Fz dz. And we want to approximate it with the Gaussian distribution. So Gaussian distribution, now we are talking about a univariate case, has the following parameters. It would have its mean, and therefore we are trying to find the mode, and it also has its variance, which we will also show how we determine it. So first we need to find the mode of Pz, which is the z 0, and that is given by in our unimodal distribution Fz, which hopefully is a unimodal, at least the dfz dz should be equal to 0, and that will define our mode on if the second order derivative at that location is a maximum, will determine that it is a maximum. So the second order derivative is negative. Now, how can we find the corresponding precision matrix, or sorry, in unimodal distribution precision, or the variance, which is a reciprocal of the precision? So we can find it by considering the Taylor expansion series of ln fz. So the Taylor expansion series takes into consideration a functional value at a particular location, and then it considers the derivatives which should be able to determine the approximation at another location from on that function nearby. And that could be calculated with an approximation with the first two derivatives in the following way for the ln fz. So we calculate the ln fz0, and that is at our mode, and then we calculate the first order derivative and multiplied by c minus c0, and then the second order derivative, which is the second order derivative multiplied by 1/2 and z minus 0 squared. Well, as it turns out, we are at the mode with the z0, so in fact this term, the derivative of this of the f z0 will be equal to 0, because the derivative here will be equal to ln outer ln f, and that will be 1 divided by the f 0, and then times the f, the derivative of f with respect to z, and we know that that is equal to 0. So this term will in fact become 0, so this term will become 0, and therefore we do not have the first order derivative term in this Taylor expansion series, and we would have only the second order derivative, and we can simplify that there is a certain a, which is a scalar value here, and that a is equal to the second order derivative of this function of the ln f at the point 0 with respect to z, z0 with respect to z, and so the a is equal to the minus of this second order derivative here. And if we have already this kind of representation here, we can recognize that we have in the logarithmic form, we can get rid of the logarithm, and we will suddenly realize that our f set is approximately fz0, and then we have the e powered by a divided by 2 z minus c0, which shows us clearly what is our approximation of the function, what is the normal distribution. The a, the scalar in this case, will become the precision of this approximating distribution, and we can observe that this function might be having slightly different value here, but it will be roughly similar to the scaling factor here, so that this distribution, the approximating distribution with the normal distribution, the distribution QZ, will be properly normalized. So this is the normalization term of our normal distribution, and this is therefore the approximation of the distribution we are we have been looking for. The same we can devise for the approximating distribution, where the z is not a scalar or univariate, but we have a multivariate distribution. So the pz is still the 1 divided by z, so this is still a scalar value, and of fc, which is a scalar value, but it takes in a multivariate or vector of the z as an input vector. The capital Z remains to be the integral of the function c dz, and we are looking for approximating it with a multivariate Gaussian distribution. The process is very similar for finding the mode of PC. We want to find it in such a way that the gradient at the f0 is equal to 0. So this way we can then find the value z0, which will turn then to be the mean of our multivariate Gaussian distribution. How to find it? There could be several ways depending on the actual distribution we are dealing with. However, we can employ some iterative scheme to find the root of this gradient function. Then we will again employ the Taylor expansion series, and we can see that in the similar way of lnfc, where the lnfc is again equal approximately to the lnf z0, and then plus the second order derivative term, because the first order derivative term will be again cancelled out, and we will end up with the formula for the square z. So z minus z transpose, and then matrix A z minus z. So the matrix A is our precision matrix in our approximating multivariate Gaussian distribution, and it can be calculated as the Hessian matrix of f at the point z0. So Hessian matrix, as we learned before, is the matrix collecting all the second order derivative terms, and if we want this matrix to be representing a maximum, then it will need to be positive definite matrix, so that as it is here a maximum, second order derivative of maximum is negative in the univariate case, and as we have here the minus, then the A needs to be positive definite matrix. If we again exponentiate the left and the right hand side, we will come to the approximation that the fz is equal to fz0 times this exponential term, and then we will again find our normal distribution qz, which will have our exponential term unchanged, but we will have here this scaling factor so that this distribution is properly normalized. And here on the right hand side, you can see an example of such an approximation. So you can see that in the yellow, there is this one function which we are trying to approximate, and it is a distribution which is unimodal, but it is not very symmetric, and we are performing an approximation with the Gaussian here. The Gaussian, we have found its mode, and then we are finding, based on the second order derivative of the Taylor expansion series, we are finding its variance or precision, and we can also somehow understand that this variance is highly related to the second order derivative or the covariance matrix or the precision matrix because when we are using this second order derivative for the approximation, the curvature at that location is basically determining us the precision. So the higher the curvature, the higher the precision value will be, and that means that we are effectively utilizing this curvature for approximating our variance of that underlying distribution and determining the variance of the Gaussian distribution we are approximating with. And in the bottom figure, you can see the negative logarithms of these corresponding curves, so of the Gaussian and of the contour of this yellow lobe, and we can see that the values are in the negative log, they are becoming the same at the mode. The mode is the same, and also if we are carefully looking here, the curvature at this location appears to be the same. Other than that, we can see that the approximation with the Gaussian is really an approximation, and it doesn't match this underlying distribution perfectly. Another use case we can see for this Laplace approximation technique is if we are interested in the model evidence, so evaluating whether a certain model is a suitable model for our particular task, and whether it is not overly complex or whether it is not matching our values very well. In the previous case, while we were performing this approximation, we actually didn't really need the normalizing factors capital Z, which is equal to the integral of the fz dz, because we were able to find the normal distribution parameters, the mean and the variance, or the covariance matrix, or the precision matrix for that matter, without needing the z value, the normalizing factor. However, we can express it here, and what it is if we have the approximation again in mind, it is equal to fc0 and then times the integral of the of this exponential term. Why is it so? Well, the fc is approximated by this function fc0 and then this exponential term, however, we can take out this this term out of the integral, and then we have only the exponential term in the integral, and therefore our z will be equal to the fz0 and times this exponent, which we can integrate into this into reciprocal of our scaling factor, so that this distribution would be properly normalized. So the reciprocal of the scaling factor is then 2 pi, which is powered by m½ and then determinant of the covariance of the precision matrix A, and then 1/2 of that, the powered by the square root. Sorry, and then with that we can use this as because we can realize that this integral is also, if we are looking at our posterior distribution determination, it will be the posterior divided by the sum or integral of the posteriors it will be the joint distribution divided by the sum of all joint distributions at the posterior, and this integral basically represents that. So we can approximate the model evidence of a data set T and modulus Mi with, carrying parameters or associated with parameters theta I, such that we will have the likelihood function, probability of the data set given the parameters of a particular model and the prior, which is determining as the parameter values will determine the model evidence. So here we have our equation for the model evidence, and we can associate that that this term here is in fact our function f. So this multiplication of the likelihood and prior is captured by the f of z or f of theta I, And in such a case, the Z is actually performing as the approximation of the model evidence. And we can see that if we perform a logarithm of the model evidence, then we will have here the logarithm of the likelihood using the posterior maximum posterior estimate of the theta parameters given a certain model, and then the prior using the maximum posteriori estimation of the theta and the terms which come from this logarithm of our a normal distribution, or at least of our exponential term here. So here we have one part of this exponential term integration, and here we have the other part. All these three parts here will be somehow compromising the complexity of the model. So the higher the model complexity is, the worse these values will be, the more negative these values will be, and this is the likelihood function, which will be somehow associating how close is the given model with the best parameters representing our data T. So our precision matrix, which we have obtained from this approximating distribution, will be representing therefore a Hessian matrix of the logarithm of the likelihood and the prior, and in fact it will be therefore approximating the logarithm of the posteriori distribution using the maximum a posteriori estimate of the parameters. After we became familiar with the Laplace approximation, let's turn to the Bayesian approach to logistic regression, where we can effectively use the Laplace approximation of approximating a distribution with a normal distribution. So, and the reason is because the Bayesian inference of logistic regression and the predictive distribution is intractable to solve the integral due to the normalization term and also due to the nonlinear sigmoid function. So therefore, we use instead Laplace approximation to approximate this the integral, and with that find out the Bayesian view on logistic regression. So we will show here only the two-class scenario, and we will start with having as the goal to find out the posterior probability distribution, which should be then approximated by the Gaussian. And therefore, we will define also the prior as being a Gaussian with some fixed hyperparameters M0 for the mean and S0 for the covariance matrix. So our posterior will be therefore proportional to the product of the prior and the likelihood function. So here the prior is our multivariate mean, and the likelihood function is, as we have seen it before, it's the product of the individual sigmoid functions represented by the yn, powered by either 1 or 0, depending on whether the yn in the training set belongs to the class 1 or it belongs to the class 2. So, and we would like to estimate the W, which corresponds to the maximum a posteriori estimation. So with this, we will therefore first perform the logarithm of this posterior distribution, which is equal to, so with the logarithm, we are having the exponent expressed from the normal distribution here, and here is the term from the likelihood where the exponents tn and 1 minus tn are multiplying the logarithm of the yn and 1 minus yn. The rest, we like all the normalization terms, we now aggregate here into this constant c. Now we perform the derivative of this posterior distribution, where we can see that this posterior distribution will, as we have seen before, this term will be, the derivative of it is this term here, and then the term for the this cross entropy error, as we have termed it as well, is equal to this gradient of the cross entropy error, as we know from the previous lecture. And this is equal to 0, but this doesn't really have a closed form solution, and therefore we will be searching for our maximum a posteriori estimation of the W using the iteratively weighted least squares, for which we need to also estimate the Hessian matrix. So the Hessian, therefore, is equal to the negative log likelihood and the derivative, second order derivative of that, where we can see that this term, second order derivative with respect to W, will be only the matrix S0 inverse, and then the gradient of the cross entropy will be represented by this term here, where we can see that we have actually forming here this design matrix transpose times the diagonal matrix times the design matrix plus the inverse of our covariance matrix from the prior. The matrix R, you may recall, is having in each along the diagonal the corresponding yn and 1 minus yn terms for each element of that, for all rows of this diagonal matrix. Now we have also the calculation here of the iteratively weighted least squares, which looks somewhat similar to the previous definition of the iteratively weighted least squares, except that we have here this Hessian matrix, so which looks slightly different than what we have seen previously, but it's obvious that we have here also this prior added, and therefore our Hessian matrix will, or its inverse, will be slightly adapted. And then also we had this other term, which was previously this design matrix transpose y minus t, but it also has this again term from the prior, and we can see that the W is of course on both sides of this equation, and therefore we are performing iteratively the calculation of the W. Once we converge such that the W tau plus 1 is approximately equal to W tau, then we have found our W maximum a posteriori estimation, and this will be the mean of our Laplace approximation of our posterior. So we would in that case find the mean, and what remains is to find the covariance matrix. And the covariance matrix is simply the inverse of the Hessian matrix, where the Hessian is calculated as we have seen before here, and the and the inverse of the Hessian is simply inverse of this of that term here. And therefore, our approximating distribution, posterior distribution, will be simply the normal distribution with the of the weights W, and the distribution will have the mean at the W maximum a posteriori estimation, and will have this Sn as the covariance matrix. Once we have obtained the approximation of the distribution of or probability associated with the weights, various weights W, given our training set, we can express the predictive distribution. So the predictive distribution, where we have a new input vector x, which is transformed with our basis function phi, the probability that this of being member of the class C1 given this input point and the training set is equal to the integral of our probability distribution of the given feature vector given a certain weight. And this weight itself is weighted with its own probability, which is coming from this Laplace approximation, which is our normal distribution, which we have calculated previously. And this function itself is our sigmoid function, where we have our weights, which is weighted with their own probability, and the feature vector, and this outcome is our well-known sigmoid function for two-class classification. And this is multiplied by simply the probability of the weight vector itself, and this is integrated for all the different weight vectors. Now, in order to solve this, we will need to make several approximations, but before that, we see that this is a posterior distribution, and therefore the posterior distribution of the class 2 is here 1 minus class 1. And now, in order to find out what this integral is equal to, we will follow the following logic. We will first change the vector variable W to a scalar A, such that the vector, which is our activation, was such that the vector W transpose and the feature vector is simply A. And we will use the so-called Dirac delta function, which is this small delta, in order to calculate, make this change of a vector into a scalar in our integral. So if we look at our sigmoid function, which is equal to the A or the dot product of weights with the feature vector, we can express it that it is equal to an integral of this Dirac delta, where we have the A minus and then basically its own value. However, the A is now here changing values. So this is a fixed scalar, but this A is changing from minus infinity to plus infinity, and the same here. However, this Dirac delta function is equal to 0 everywhere else except of when its argument is 0. So when the A is equal to this function, this Dirac delta is equal to under integral, so integration of this Dirac delta itself, is dA would be equal to 1, the result of the integral. We can, for example, imagine that we are limiting this the borders of integration from minus infinity to plus infinity just to something very close to 0 from the negative side and something very close to 0 to the positive side, and that is the only moment when this is not not equal to 0, and in such a case, as this is infinitely small integral, we can consider this function as being constant, and we can take it out of the integral with its value. Actually, it will not be close to 0, but close to W transpose phi x, so that this all argument is 0. So we can take out the sigmoid with the value W transpose phi x out of this integral and integrate this, then has been equal to 1. So therefore the left side and the right side are the same. At the same time, we define a probability of A, so some function here, as the integral which has a similar structure. However, it has not the sigmoid. I mean, it doesn't have the sigmoid in here, but it has the Q of W, our normal distribution approximation of our posterior probability of W with respect to T. So now, if we look at our integral, which we have here, that one is equal to, we replace this part with the integral and this Dirac impulse and the sigma ADA. And now we can also remove these brackets, have it as a double integral, where we will have both W and A as integration variables. But then we can also put another part into the brackets, namely the part with the Q normal distribution with respect to W, and we can see that this part is in fact equal to the PA. So we have, therefore, this integral will be equal to integral of PA times sigma A dA. Now let's have a look at the relationship between the W and A, or the W transpose phi x. So if we have the following condition here, this condition is forming a so-called linear constraint where this is fixed to the phi x, and our W vector, in order to have a dot product which is equal to A, is constrained on being located on not entire W space of the dimensions as many as the W vector have, but actually within this space it is constrained on a hyperplane that satisfies this condition. And within this hyperplane, we can imagine that if we add any vector u which is orthogonal to our feature vector phi x to the W, so any of these vectors u will be again forming the same, as this is this dot product here is 0, it will form the same dot product as before. So therefore, it will be still equal to A. And all these vectors u, which are perpendicular to the vector phi, will therefore, as being added to the vector w, will be forming us the hyperplane from which the w's can be chosen. So if we look once again at this formula for the PA, this Dirac delta is where is it 0? It's 0 almost everywhere, except of when the A is equal to W transpose phi x. In that point, it is not equal to 0. So everywhere else, if the W is, if in this integral, if the W is not equal, W transpose feature vector x is not equal to A, this will be automatically equal to 0, and only those vectors W will be considered and multiplied with QW, which are laying on the hyperplane A equals W transpose phi x. So the distribution Q of W is our Laplace approximated posterior distribution of the weights, or the probability associated with particular weights. It is a Gaussian, and it is the Gaussian is placed in the W space with all the W coordinates and the corresponding dimensions. However, if we are performing a linear transformation of Gaussian, it is also a Gaussian. So if we are having our distribution Q, which we are looking for, it's W. So its mean is the W map, and the covariance matrix is Sn. Then then for a where A is equal to the W transpose phi x, so this is the linear transformation, the probability distribution of A is a univariate Gaussian, because this will be a scalar product as a result of the linear transformation. So we need to, as now we are looking at the PA instead of the QW, we want to find out what are its characteristics, what are its parameters, mean and variance. So for the mean, we can it's an expectation of A, and then therefore expectation of A is equal to the W transpose phi x, and that is equal to W, this is the feature vector x times the expectation of W. Expectation of W is the expectation of the distribution QW, and therefore it is the W map transpose, so maximum a posteriori estimation transpose times the phi x. So this is the mean for our linear transformed Gaussian, our univariate Gaussian PA. So that is the mean of it. We have one parameter. Now let's try to find out the variance. parameter where the variance of A is equal to the expectation of A squared minus expectation of A and that whole term squared by definition, and that is equal to now we are putting in the actual term for the A, which is W transpose phi x squared, and then we have minus, and then we already can put the expectation of A squared is this term. And then we can multiply out the squared terms, and we will end up in this term here, where we have effectively two dot products. And here we have again two dot products. Now, so what is this equal to? We are not yet done. Let's define that we have an random variable epsilon, which is having the mean at 0 and has the same covariance matrix as our vector W or as our QW distribution. And then in such a case, we can formulate that this term, which is here, this is equal to, in fact, the W is W map plus epsilon. So we have a certain offset from our mean, which forms the W. So we only replace that, and that is equal to, and now we can multiply that out into three conceptual terms. One is the W map phi x transpose W map, and this expectation is actually equal to the argument itself. So we have it here. Then we have the two cross terms where we have in argument the dot product, two dot products. However, the epsilon has the mean 0, so that will lead to the fact that this whole expectation will be 0 for both of the cross terms. And then we have the final expectation of the epsilon transpose phi, phi transpose epsilon. And what is that equal to? So we can have a look here for these terms. We can perform this so-called trace trick and rearrange our elements, and we will end up in representation of the trace, which is O transpose, if we have here some kind of O vector, and E as epsilon transpose in the expectation. And that is equal to the O transpose expectation O. And this term here, we can see here that for the random variable Z, expectation of Z transpose is equal to the covariance matrix plus the outer product of the mean. The mean is 0, so it's only the covariance matrix, and that is in our case Sn. So we will end up that this term will be therefore relevant for our finding out what is this term equal to, and that is simply equal to the phi x transpose Sn phi x. So, and when we add this, when we put this instead of this term here, we realize that this term itself is cancelling out with this term, and we are only left with the phi x transpose Sn phi x, and that is in fact our covariance, so we can see it here. So this is the variance, and here is our probability distribution of A, which is a normal distribution with its mean and the variance. So now we can finally come to expressing the predictive distribution for the phi new input vector x and the probability of a given class given this phi x and our training target values t, or the vector. And that is equal to the integral of our Gaussian linear univariate Gaussian distribution PA times the sigmoid ADA. Unfortunately, the sigmoid function is not easy to integrate, and therefore we will perform a certain approximation. We will approximate the evaluation by replacing the sigmoid function with an inverse probit with a similar shape. And with a similar shape, we can see here that there are two functions. One of them is sigmoid, another is the probit function, and this probit function is so essentially the relationship between these two, sigmoid A, is approximately equal to probit lambda A, where the lambda is pi divided by 8 and the square root of it. So once we have this, we can represent the sigmoid instead with this probit, and the probit function can be in fact integrated with the normal distribution, because the probit, you remember, is the cumulative distribution function of a normal distribution. So these two can be well integrated, and the outcome of this integration will be again a probit function. So let's have a look at how this can be done. In order to perform the integral, we first, so this integral here, we first need to perform some substitution, where we substitute the variable a, random variable a, with the mean of our normal distribution, and plus a random variable omega and times sigma. And so the standard deviation, and therefore the dA is equal to d omega sigma n, and therefore omega is in this case, given this representation, omega is a random variable distributed with the normal distribution with the mean 0 and the standard deviation, so variance, equal to 1. So therefore we can perform this change, and that would mean that here we will have this standardized normal distribution, and here instead in the probit we would have this replacement or substitution of variables visible, and that will lead to a formulation which is possible to integrate with some standard results, where the probit of lambda a plus b omega is times the phi omega. So this is the cumulative distribution function. This is the probability density function of omega, this one. So that's the phi meaning here in this case, and that is equal to the probit of a divided by square root of 1 plus a beta squared. And we can use this result, and therefore our result here will be lambda times the mean of the normal distribution, and divided by 1 plus lambda standard deviation squared and square root of that. And that is the probit function. And in order to obtain the corresponding sigmoid function, we can simply express that probit lambda a, so we can consider this as some kind of a, is equal to sigmoid of a. So therefore the sigmoid function is simply this function by this temporary substitution of the probit function into solving the integral, and then we have the result of our sigmoid, which is the predictive distribution of for a probability of a class given new input point and the training set. So for that we have we can put in all the variables we know. So we know that the mean is the W map, which we have obtained before by the iterative reweighted least squares, and also times the feature vector x, and then we have here 1 plus, and we have the lambda here, which is the pi divided by 8 times squared, and then we have the phi x transpose as n phi x, and that is the square root of this term, of this whole term. And that is the result of our Bayesian logistic regression, the predictive distribution, which takes into account all the weights W and their associated probability distribution, and calculates the probability of a given class in the two class case for a new input vector x. And this is also the end of the chapter on classification, and we will continue with the next chapter on neural networks.